Hi everyone, my name is Danilo Pau, and well, thanks to join me and all the speakers and TinyML Foundation for this exciting forum, which is going to elaborate even more the topic of generative AI at the edge. So we are going to go beyond large language model and chatbots and continue our journey to see what's happened and the evolutions of generative AI at the edge. So we are going to have a great list of speakers today and tomorrow. But before to introduce each speaker, I would like to thank on behalf of the Technical Program Committee, Pete and Davis, the strategic partners, which are giving us all the support we need enthusiastically to make happen these and many other events. So thanks to all the strategic partners and thanks to TinyML Foundation for all the support, the initiative, the energy, in particular to make it happen this exciting event. We had a first forum on March. It was chaired by Davis Sawyer. Thanks so much, Davis. You did a great job. I was really impressed by the forum that you chaired, and at the point I felt the urgency to start to do something on the topic of generative AI. So it was very inspirative. There was a huge attendance, 730 attendees, and with a lot of questions, which remarkably underline the interest that the topic is representing for all the community. And there are all the video and presentation available, recorded and stored on YouTube channel. There were a lot of discussions, so you may want to review all of these later on. But really, the work that Davis did helped to very much to create let's say, to create the ground for the next forum, this one. So what we are trying to do today is continue to understand the state of the art of generative AI at the edge. What does it mean? What is the edge? Does it exist already, or maybe will exist? Which means that there will be a transformation. So what kind of transformation are we looking at? On algorithms, on software, on chips, on silicon, on tools, on applications, on methodology from EDA standpoint, but as well as how to design generative AI workloads at the edge. So these are really the things that we are eager to look at them, and we would like to hear more inputs from our speakers. And obviously, we would like to get inspiration. There will be evolutions. The first forum really gave us the push, the energy to start and to move forward on generative AI at the edge. Certainly, people activated, like me, like many others. Certainly, people are working in these directions. And so we needed to hear from them and understand how generative AI is going to impact the edge, as we know is fully deployed on the cloud as it is today. But we want really to democratize, to make generative AI for the masses. So we need really to understand and to look what transformation are happening. And the final objective is to inspire the community all of us represent. Thanks to TinyML Foundation, which created an awesome community, then we need to exchange our developments, to discuss and exchange our idea, to inspire many others, because ultimately we want to move forward all together and show the impact of innovation, which certainly will be huge. And generative AI at the edge is expected to be a huge and breakthrough technology impacting everyone work and also life. So today we will start with a great speaker list. I would like to primarily thanks Dave, Roberto, Chen, Alok, Seung-Yang, Arniban, and Alberto to have accepted to be speaker with us today and to share their point of view from a technology standpoint, but also from the context of how this technology is changing the TinyML landscape. And last but not least, I would like also to thanks a lot Pete Bernard and David Sawyer and Rosina. All together we set these 2 days in an outstanding way, and I hope you will enjoy. Having said that, I would like to leave the floor to Dave McCarthy and Pete Bernard for the first lot and the first presentation titled How LLMs and Transformer Models Will Accelerate Edge Computing.
Fantastic. Thank you, Danilo. I'm going to bring Dave on here and we'll take your slides down for a second. Fantastic. All right. Here we are. Hey, Dave.
Hey, Pete. We certainly are.
Let me bring up your slides. So as everyone knows, this is a live stream. So it's an all day long live stream thing, or I guess for folks in Europe, kind of all evening long. So apologize for starting at like 5 p.m. there. Yeah, and let's just kind of bring up the slides and, you know, kind of let's see where we're at here and have a conversation. And I think that'll be fun.
Sure. I mean, to introduce myself, my name is Dave McCarthy.
Yes,
I'm a research vice president at IDC. And for anyone who's not familiar, IDC is a market intelligence and advisory firm for the tech industry. And believe it or not, we've been doing this for over 50 years as an independent voice to understand what's happening and changing in technology. What does it mean for both people who are building solutions and people that need to deploy those solutions? And so we have over 1,100 analysts worldwide. I have the pleasure of leading our edge computing practice. And so what I thought, Pete, we could do today, I have a few slides. I thought what would be helpful is to give a little framing of where we are and where edge computing fits into the bigger world, and then maybe tackle a little bit of the question of, you know, what is edge, and then, you know, maybe get into some specifics. How does that sound from your perspective?
I think that's good framing because we're going to have 2 days worth of pretty intensive talks. And so setting the context here would be important.
That's what I thought, right? There's going to be tons of deep dives. So to start off, when we look at it from IDC in terms of where people are investing and where their priorities are in infrastructure for 2024, we've put together this framework, and we believe it's really based on these 4 pillars. I mean, certainly I just came out of a big user conference at IDC, and everybody is talking about this idea of like AI ready infrastructure. And in the cloud, of course, this makes a lot of sense because people are moving from general purpose types of cloud instances to more GPU enabled and things, not just on the compute side, but storage and networking. And so we're looking at the changes, right? Like how you're building going forward is probably gonna look very different than what you built on in the past, right? So that's the first one. The second is around autonomous operations. When you think about the scale of what we're talking about here, whether it's scale of like scaling up in terms of just big training clusters, or I'd call it maybe scaling out of all of these deployment locations, you're not going to want to do this behind a set of dashboards, and you're not going to want to do this with buttons and manual, right? There's going to be a heavy level of automation involved. The lower left, of course, is the point of today, is this idea that whatever you're building has to have the idea of edge designed in or optimized in. Because as Danilo said, right, there really is this continuum. And I'll jump right to the answer is, you know, is edge real? It's absolutely real. And we have so much market data and proof points around what people are doing. But it's not just the edge side, right? It's also where do these other deployment models around things like hybrid and multi-cloud fit in? Because what we've seen is it's so easy in the industry to talk about things that sound singular, right? Like we talk about cloud and we talk about edge, but nobody has just one cloud and nobody has just one edge, right? And so you take all these kind of things and you sort of build them around concepts around trust and security and sustainability that's really important, and how do you build resiliency and agility into how you do things. And And you want to wrap that, of course, in knowledge in your organization. That's probably going to have to be cross-functional in many ways, which is why we kind of use that term center of excellence. This is the framework, right? So Pete, like when you're talking to people, I'm imagining nobody talks about the things that they do out in the field in isolation, right? It's always part of a bigger aspect.
Yeah, it's definitely a multi-cloud, multi-edge world out there. And in fact, when you talk to kind of Fortune 500 about their actual solutions, it always involves lots of different components from the cloud to the edge, right? It's never one piece of equipment or one chip or one thing. So it's always a blend. And in fact, I think this idea of like stitching together AI workloads from the edge to the cloud, especially if you're running more kind of generative AI and things like that, it's definitely going to be kind of the new frontier.
Yeah, it's incredibly important because I feel like even when we hear about how people design, it's one of the nice benefits, by the way, of moving to that cloud native design principle. I mean, that's where some of the agility comes in, where since you no longer are dealing in most cases with big monolithic types apps where it's like it either runs here or it runs there. It's kind of like it runs here and there, right? And I feel like all these companies are trying to figure out how to take what maybe they built in the cloud and extend the things that are really important. So this was kind of the first sort of, hey, here's the world as IDC is seeing it right now, and investment areas. So from there, maybe we should just tackle head on.
What is edge? This is always a hot topic for me. People always
is, right? I mean,
on.
and I remember, so like I joined the company 5 years ago to be an analyst for the very first time. Prior to that, as Pete and I found out, we never worked together directly, but we always worked sort of in the same circles. And it was either the term embedded software or IoT was probably some element of that. And I certainly spent a lot of time working at a company that was a Microsoft partner, focused on the embedded operating system space. And so, and not just on things like microprocessors, but microcontrollers, right? Where it was all about, there's different sizes of how you start deploying when you get out into the field. And that's really, to me, where I was first introduced to this idea of edge computing. It's like, well, you have resources available. So why wouldn't you take advantage of those resources to do things? And so to me, that's why there's sort of like one of the challenges I had when somebody would say, hey, there's 10 different definitions of edge. It was often because people would say, well, it's all about the dimensions they use to describe it. Like people would talk about, and even us at IDC, because we have to categorize things, we would say,
right,
well, you might have a big Dell server sitting in a factory. So that's an edge sort of scenario, but we call that a heavy edge because it's like a Xeon based, lots of resources. Right. Or it might just be a gateway that's aggregating data, maybe doing some filtering and moving it on. That'd be like a light edge, right? That was one way to talk about it based on like capacity. Then I feel like you got to the point where it was like, well, there's that locational view. Is it a near edge and a far edge? To be honest, I didn't really like that one because it's so subjective. Like where you stand depends on where your near and far is. But it was important to understand kind of the fact that back to that sort of layers, right? It's like layers of edge. And the great example of like that I would think about in those IoT days, especially like we'll just use like the factory environments, you might have a control system connected to a machine, and that's like that's one layer. And then you would have a gateway within that building that was aggregating data from multiple machines, right? That was like the next layer. And then depending how complicated your environment was, you might actually have regional aggregation points, right? And then you rolled it all up, right? But that was part of that, those sort of layers. And then maybe finally just, because we could go on forever, but you started hearing people think of it in like the industry perspective. Like, is it a retail edge or is it a telco edge? And so when I was tasked or challenged with like, how do you create a definition that's sort of inclusive of these different scenarios and reflective of what I think the purpose of edge is in a lot of these scenarios, it was these two sort of like blue kind of bolded areas here, which was this move away from centralized to distributed. And, in the decade before that, it was all about data center consolidation and move to cloud. So while these weren't novel concepts, it was sort of a change in direction, again, of bringing this out. And it was because of where IDC was seeing data generation. We also have this huge data set and analysts that sit around and try to figure out, where does all the new data come from? And where is it going to be? And it wasn't too long ago that we realized that we're seeing more data generation outside of data centers than in the traditional places, right? And so if you have this idea of like, okay, well, centralized systems were designed around centralized data. Now you have all this data out in the field. It's that quandary of, do you take the time and energy to pull all that data in, time and energy and cost, by the way, pull all that data in to do something about it, or do you take the processing and the logic and move it out into the field, right? So that's why this like where data is generated and consumed, I think was so important. We put this definition out, I think back in the early 2020s, and I was actually really delighted when I saw a lot of vendors kind of, when you looked at their marketing, they were kind of taking some of these elements of it. That's kind of our role. But Pete, you obviously are right in the middle of all these conversations too. Like, how do you see when people talk about these definitions?
Yeah, I mean, so the question I always get is, what is TinyML, and then what is Edge AI, and what is, so in the AI context and ML context, one of the, I guess, positives and challenges of the tech industry is we kind of just make up words to describe things. And so, I really think of Edge AI, TinyML, efficient ML, Edge ML, analog AI. All these terms really mean like running AI workloads in the real world, running it where the data is created. And really, we're all about connecting AI to the real world, and that's what a lot of the companies in the community are about. And that's distinguished from running AI in the cloud, right? And I think one of the things that you're mentioning, which is a bit of a little outside of our rubric, is is that cloud near prem, on prem, or in a data center. For us, it's really like, and a lot of what we're talking about today is how do we run generative AI workloads in these devices that are, happening, that are, located where the data is being created. I think that's what you mentioned here is like, that's for us is the really differentiating factor, is in a resource constrained environment in which, these edge platforms are, these tiny platforms. How do you run AI workloads effectively? And in this case, generative AI workloads. So that's kind of what I think of as this distinction, is there's this kind of AI in the real world, and then there's AI in the cloud. And that stuff that's happening in the real world where the data is created is what we would consider kind of edge AI technologies, inclusive of TinyML.
Yeah, and no doubt. I mean, originally, when we put this out, we weren't talking about it as much in the AI context. But even that's not a completely fair statement, because even in those earlier days when we were looking at, my days prior to joining IDC, when I was working on solutions for did some really cool projects for companies like Honeywell and Ford Motor Company and Coca-Cola, who were all creating smart devices that were out in the field. They wanted to be able to move the logic out there. The challenges we had at the time, of course, resource constrained devices. And that's why I kind of, in this picture, it's like, well, sure, there's going to be some element of public and private infrastructure, could be cloud-based, could be traditional. There's going to be these layers of edge, and then the endpoints, of course, in the IoT space were so important. But what we were doing at the time was, I couldn't say we were running ML at the edge by any means. What we were doing is we were taking a lot of IoT data, we were taking it back into the cloud, we were running machine learning algorithms against it to basically create models that we could extract rule sets from. And then what we would do is like run a little rules engine somewhere where we could say, okay, of these rules, here's something. And it was AI-like in the fact that it was like, wow, intelligence that seemed more tuned to the data, but it wasn't the same, right? I mean, I think that's the difference between, I guess, the technology we were working with 5 years ago to do some of these and what's available now.
Right. Well, and inherently, once you start this distributed, computing paradigm, as you mentioned here, the idea of management and orchestration becomes super critical, right? So now you've got multiple systems, as I mentioned, kind of stitched together. And how do you, provision workloads or retract workloads or update things? That's what the IoT business had been struggling with for a long time. But now you add a little more complexity because you now have AI models that need to be either provisioned or updated or run on different things. So the kind of orchestration and management of things that are connected becomes really critical. So
yeah, and that was part of that pillar around that sort of autonomous operations, is because once you move out of the lab and out of the POC, now all of a sudden you do have a management burden of how to do all this.
Exactly.
When we were kind of putting together some of the reasons why edge computing became really important, this would become the, like, why do this, right? I mean, this was one of the things that also, in those early days of trying to manage, connected devices in the field and take advantage of the data, there was always this, question of, like, can't you just do that in the cloud? And that was one of the things that I saw early on. You started looking at, from the technology side, whether the bandwidth requirements around some of the things you wanted to do became sort of prohibitive because you're dealing with environments that might have limited or disconnected systems, or that latency thing, which was so big. And when Edge all of a sudden kind of came out of the shadows and people are like, well, hey, that's important. The resiliency in operations, I think, is actually sometimes an underappreciated one, because of the fact that we've all seen, and I work with all the cloud providers, and so they'll know I'm going to say this, right? They all have outages. There's still network, issues. But most importantly, that scalability aspect of things. I think that all of those kind of come together as like, well, you want to take advantage of this as part of your overall design to try to do that. And of course, there was business side of things as well. I mean, people looked at some of this, like, if you could take advantage of knowledge and make faster decisions and be smarter about what you're doing, how does that help you improve products and services? And of course, so much, the reason why I brought up that whole, like, the vertically specific edge, is that that's where a lot of differentiation is happening in the market today. I mean, everybody can run the same kind of homogenous app in the cloud, but when you get into that retail store, or you get into that factory, or you're doing something interesting in transportation, or whichever the industry is, like, that's where those touch points happen. It also allows you to, like, get more tuned on things around innovation, and the security thing can be interesting. And, of course, looking at stuff like, like limiting the movement of data sometimes, or being smart about what data you keep and what data you don't keep. Is incredibly important, right? Like, these were some of the things that continued to pop up. And, and I say this, that, like, not everybody is going to sit there and say, yes, I've checked every box on both sides of this thing. And that's perfectly fine, right? I mean, these were just areas where we saw concentration of, like, when people were making the business case, or saying, like, here's why I should do this, or proving ideas for the tech teams, right? So these were some of the big ones.
Yeah, we say, like, every AI project starts on the cloud, as kind of an experiment, and then as it gets commercialized, it tends to migrate toward the edge because people want to cost reduce it and add in, security capabilities and other things. And it's like, well, how do I, do this in more of a CapEx environment than a purely OpEx environment? And so that tends to be sort of the gravitational pull toward the edge, as I call it, for these AI workloads. But we had a session recently with someone from the city of San Jose talking about smart cities and critical infrastructure. And especially when you're talking about AI vision and a lot of edge AI vision scenarios, you can't stream videos from a street light to the cloud and process them. You need to be looking at, for pedestrian safety, for example, in real time, and acting accordingly. So that's really scenarios where you have sort of high bandwidth data that needs to be acted upon pretty much instantly. And, maybe there's some archival stuff you can send up to the cloud at some point, but the ability to kind of act on the data in real time where the data is created is so critical across agriculture, smart cities, critical infrastructure, healthcare, water systems. I mean, you name it. So it's definitely now what we're seeing, and what we're going to hear about, the next couple of days, is all the new capabilities that are going to be possible in terms of running generative AI and sort of token development stuff happening, on devices in the field. So it'd be pretty cool.
Yeah, certainly. And so one of the things we do at IDC, aside from besides all this, I didn't want to bring that today. I didn't think showing everybody how big the market was going to be from a dollar perspective would be the most interesting thing. But what I did think would be interesting is, kind of a look at, you mentioned about, like, workloads and like workload placement. And so we do on a regular basis, like, big surveys that are global in nature, and we really try to get to a bunch of different questions around, like, some of it's motivation, some of it's how they're going to do things, and some of it's, like, the why. And so this particular question, which we put out earlier this year, which was, what's the best estimate of where your organization is going to be deploying Gen AI workloads across that sort of digital infrastructure over the next 18 months? And, the punchline here is it's everywhere. But, look at that heavy emphasis on the end, worldwide, right, is that first column, 20% saying that these are going to be, it's kind of a catch-all, right, of these sometimes edge, branch, small locations, maybe still bigger than what you're thinking in the TinyML space, but I would include that in that number too. The important part here is that I see awareness, right? Like, I see that, like, if this was like 90% pegged to public cloud, then I would be like, this edge thing isn't real. I think there's been enough experience on this now that they're realizing that that edge is going to play an important role. And in some breakouts here around how we look at it from regions, but To me, this is that big difference between, Pete, you said, want to make it real, right? Like, and it is true that, everything in the cloud is kind of, it was always the point of the cloud was like, well, hey, you don't need to know where it is, and it kind of does things for you, and isn't that great? But and if I think about where we are in the AI conversation, especially the Gen AI conversation, it's still dominated by the LLMs and big training. And so, of course, we're going to continue to see, so who's got the big? It's like the race for the biggest cluster. I've got
how big
the biggest
can you
trillion
go?
perimeter model and everything that's like, right? Like, so let's let that war happen, because I think it's going to be interesting, and there's going to be some winners and losers, and certainly there's going to be a lot of money spent on trying to figure that out. But very soon, we're going to start hitting that tipping point, to the inference side, to this idea that, okay, fine, we've got the models, we've figured out our strategy for this, but we need to deploy it out in the field, like make it real, right? Like get it out there. And when you get it out there, that's where that infrastructure hits all the things that anybody in the embedded software space has known for a really long time, which is like constraints, constrained anything, right? Constrained memory, processing, network, power, right? In the case of battery powered devices. So are you surprised to see this much recognition?
No, I mean, that's good to see. I mean, that's actually higher than I expected. I think, going back to your point, these days when people talk about AI, especially in the general press, it's about how big can you go, like you said, the trillion, whatever. But all this training stuff is still happening on the cloud and will for some time. But training is cost and inference is revenue, right? So the training can happen in these big data centers, but like you said, when you actually want to use it and inference on it, deploying that out toward as close to where the data is being created as possible is kind of where the gravity is. And I think the only thing that's going to stop folks from going all the way to the edge are just the capabilities that we'll talk about in the next couple of days, the amount of memory that's required, or the amount of TOPS or horsepower, or devices and things like that. So I think, thinking about the training in the cloud and the inferencing at the edge with reinforced learning at the edge is really where things are heading. And it's great to see, at least even now, the awareness. Because I would say most people, when you think of generative AI, there's a very small subset of folks that are thinking about it on the edge, probably the folks here over the next couple of days. But it's great to see that awareness internally too. And I think as there's more kind of press and coverage about what's actually possible on the edge, we'll get more and more companies that are interested in deploying it there.
Yeah, and I think the challenge, and again, to be clear and transparent, that edge number includes everything from server-based like edge systems to very tiny things. And in my experience, I would say where this might be why I'm surprised the number is so big, is I guarantee people haven't figured out how to get Gen AI on small things, because right now it doesn't really seem necessary, right? If you're just going to communicate with a LLM and you can do it through a web page, it's just like, well, why would I need that local? But what we are seeing some examples where people are now looking at that in that more distributed way, and it's always a march outwards. I mean, at least that's what I kind of think about this. And so I feel like the good message is that people are aware of this. They're starting to build it into things that might look like big edge locations, but ultimately they'll hit those same bottlenecks. I'm sure the things that TinyML is working on to, again, get it all the way out to those endpoints, including the extremely small ones, because I feel like it's a lot of where we feel the value is how you kind of build all this in some sort of a, again, it's like a continuum, right? So you want to make sure that you've got addressability at all points along that.
Yeah, definitely. Hey, by the way, we have an interesting question. I just wanted to bring it up for a second.
Okay, sure.
So just to clarify kind of a definition of terms, Ion asked, are we targeting SLMs, what we call small language models, in the TinyML or in edge computing? And again, this is a bit of a terminology thing, but edge AI technologies in general is what we're talking about today, and how we would run generative AI or transformer-based architecture. So, I don't think anyone's expecting, maybe we'll be surprised, but I don't think we're expecting, SLMs to be running in MCUs like Cortex-M based chips anytime soon, but they would be running in, MPUs or things like that would be considered kind of edge AI and edge computing. So just want to clarify that a little bit. Again, we're sort of mixing up terms here, but just think about language models running in resource constrained environments on the edge, not in the cloud. And that's kind of what we're talking about here. Okay.
Well, I'm really glad that there was the question about SLMs, because guess what my next slide is?
All right.
Oh, it has something to do with small, well, this is like more small footprint models. But same idea of, if you're, a lot of what I've seen, this is just true of technology in general. I mean, it reminded me of like when people moved to cloud in the first place. It was this big, almost all of what you do when you're in technology, at least in the companies I've worked with, it's always like job one is, can you make it work? And so you make it work, throw whatever resources you have, and you all get excited when you see it, give the result that you want. And once that's done, then you get into sort of this like optimization and efficiency stage.
Right.
And when I hear about like one of the big concerns that people have around just Gen AI in general is the cost, because back to that very first slide where I talked about, well, you're going to need a lot of big, heavy, GPU infrastructure to do this, and that's really costly. And if your strategy is to query a big model on a regular basis or 100 times a second or whatever it is for you,
add up, yeah,
like that meter is just spinning in the background, right? So I hear a lot of talk about like, okay, great, like what is really necessary, to do the things that we're doing, and where an LLM, of course, is trying to answer the widest amount of questions possible. When you get into the field and the things that you're doing there, it's very much more like you want to be able to solve a very particular use case or set of conditions and things like that. And so narrowing, the things that these are doing done through SLMs or small footprint models or whatever the correct terminology will all kind of land on is important. And you can see there's a huge amount of people that are evaluating this idea. Now, again, and some that say that are already using it, that one is the one I actually really question more so than the edge one, because I'm like, okay, I believe that people are doing things at the edge. I'm like, are you really using small footprint models today? Because I don't really believe that they're out there. And this is one of the flaws that often happen in when we do surveys like this, even if we ask a lot of people. I've seen this in other places where in the early days, they're very optimistic, or, oh yeah, we're doing this. It's not a magnitude question. It just means like, well, maybe we found something and we did it in a place. Hey, maybe we're working with TinyML. And they said, hey, look, we're trying something out in a spot. So we're going to say, yes, we're already using it. Maybe just not using it in mass. But to me, what's interesting about this evaluation, sort of big uptick in evaluation, means this is a great opportunity to educate people and to drive awareness that, like, well, I should say the awareness is there, but the detail around what that really means and how might they go about it. And I'm sure there's going to be competing ways potentially to do this, and looking for the one that's most appropriate and has the right community support. And all of that, I feel like that's pretty much, Pete, I'm assuming that's kind of the goal of these next 2 days, is to really kind of widen that aperture a bit to say, look at all the interesting things that are happening today. And if you are in that evaluation stage, here are some new things to consider.
Yeah, for sure. Like what's possible. And, like this kind of demonstrates this gravitational pull toward the edge. Like you said, people always start in the cloud to get it working. And then when they realize they want to actually commercialize it and deploy it, they think, gosh, that's going to cost me a lot of money every month to run this thing. Maybe I can just run it on a box, in my shop or whatever in my factory. So yeah, I think it's really exciting to see that. Maybe what they're thinking about, maybe they're confusing their CNN models with their Gen AI models in terms of what they're already using. I don't know.
It's possible. And this one, we did ask. That is the other thing that's true too, right? I mean, you hear a lot about sometimes in the industry, there's so much Gen AI in the brain. I've heard this from just other vendors where they'll go in and ask a customer, tell me one of your priorities. And they'll say, well, I have a Gen AI project. And they'll say, okay, describe it to me. And then you'll find out, okay, that's not really Gen AI. It's an AI discipline. It's just different.
Yeah, it's a little blurring there of the terms, right? People think
Gen AI is, but to me, this is like one of those things where I've become comfortable with it in a way, because for people that have been around machine learning and AI for a long time, maybe you did the yawn when you're like, oh, now everybody thinks it's cool because it's Gen AI, and like we've been trying to solve these hard problems. And in fact, that's actually something I've found really interesting, is that the Gen AI conversation, I think people liked it for two reasons. One, it was like, wow, look at this wonderful out of the box thing that seems magical. I've always heard that AI is hard. This sounds like AI is easy, and so let's love it. Let's go and put it everywhere, right? And so again, good news, opened up budgets, opened up priorities, and got it on the roadmap of things. Now, of course, what I'm finding in reality is once you get out of maybe one of these predefined, pre-trained LLMs and you're dealing with your own data or creating your own things, all that hard stuff is still there, right? Like you can't avoid data cleansing and all the things that you have to do to be able to even prepare, for this. And so, I think there's going to be some reality or some reality shock of what does it really take to build some of this. And I'm hoping that the people on this webcast kind of going forward are going to offer some unique ideas on how to make that easier within certain environments. But I think that's going to be a challenge as people. But the good news is I don't think the genie is going back in the bottle. So I feel like, that inflection point, whether it was the perfect one or not, it was a useful one because it's now drawn a lot of eyes on what's possible here. And maybe people that, thought this was something for data scientists or something in the engineering group are now thinking about this more broadly of how do I use this across the business?
Yeah, exactly. Yeah. And someone had brought up an interesting comment, if we can just show it for a second, was around LPUs. So when we're talking about edge equipment today, we're talking about things that are running typically GPUs or NPUs. But there is this thing happening, more in the cloud right now around LPUs. So like building silicon that's designed really to accelerate generative AI models specifically, or transformer-based architectures as opposed to more generically. And there's this. If you go back in history, we start with CPUs, we go to GPUs, we go to NPUs. Like the semiconductor industry is building more and more specific chips to do more and more specific things over time. And if there's a market, and we're seeing some of it in the cloud, like especially for training, optimizing training clusters just for training Gen AI models. I'm sure we'll see that transition out to the edge as well. And I'm not expecting any product announcements today, but I'm sure someone at some point will have an LPU in their edge platform.
So this is my last slide, Pete. But to your question, to the question around just like hardware diversity and like silicon and what's potentially happening. I mean, I've seen some interesting things or interesting startups now that are kind of trying to solve this especially for these smaller type device use cases and things. So I don't imagine, NVIDIA of course has some, Jetson and some of its smaller stuff, but I don't suspect that, they're going to tackle some of these things. I mean, I think this is a place for the larger silicon ecosystem to kind of come in, and where startups might do some cool innovation and figure out how that gets worked into some of the broader systems. Yeah,
fantastic. Well, Dave, I really appreciate the time getting caught up. Give us some context here. I mean, it sounds like it's happening and you've got the data to back it up. I feel like we're at the beginning of many years of interesting work, and we'll see how this thing plays out. We did one of these about 6 months ago, and I feel like we need to do one of these about every 6 months, because whatever we're talking about today probably didn't even exist 6 months ago. So it'll be interesting to see how this plays out 6 months from now, and with some of these actual deployments and things. So
yeah, it's one of those where, I guess just maybe like when it comes to some of the use cases, because this is where, we were seeing where is the deployment happening? I mean, some of the low hanging fruit within Gen AI has always been those sort of workflow and very business, it's like the efficiency stuff. And people haven't really tackled the what I might call the harder ones, but the harder ones, of course, are always the more valuable ones. And so that would be a great thing to kind of keep an eye on every 6 months or so, is to see like which use cases and which industries are getting the traction now, and which might be the next up in the batter's box, because I think we're going to kind of see waves of this as the technology gets better, as people, or I say better, but more mature, and and people understand it better, and it's just like anything else, right? You have to build confidence. And once you build confidence in these systems and you see the value of them, it just makes you want to do it more. So I think there'll be a snowball effect. We have to kind of get out of that gate in a stronger way first, and then we'll be able to reap all those rewards.
Awesome. All right, I brought Danilo here to transition to our next speaker. Dave, talk to you soon. Thanks.
Yeah, thank you.
Okay.
Thanks a lot, Dave and Pete. I have also comments, and maybe later when we have the slots with you and Davis, there were a lot of good inputs from Dave to come back. So next speaker is Roberto Morabito. And please show up, Roberto. Hi. And hello. Thanks to accept the invitation and to present. So consolidating TinyML's life cycle with large language models, reality, illusion, or opportunity? To you, the floor, Roberto. Thanks.
Thanks a lot, Danilo, and thanks to the TinyML Foundation for organizing such a nice event. This is pretty much the outline for my presentation. What we will try to do is trying to essentially answer to this question and understand to some extent whether the usage of large language models can somehow help in the management and automation of the lifecycle management of TinyML. So the core of the presentation will be, of course, the introduction of this framework that we have developed between Eurocom and University of Helsinki, and we will also show a very short proof of concept and a demonstration before also providing some empirical insight on what's the type of resource consumption and the possible bottlenecks that we have observed in this first phase of the work. And what I would like to also emphasize is that we really embrace the great opportunity that we are envisioning, and this event is definitely like witnessing the great momentum that there is increasing towards more and more interesting works in the area of generative AI at the edge. And we have seen during the first series of this event, and there is a lot of work both in industry and academia that kind of showed how there is more and more effort from the research and development point of view on trying to push language models and generative AI towards the edge. But what we want to actually do with this kind of work is essentially trying to take a step back and trying to understand if there was any possibility of taking advantage of a large language model in the intersection with TinyML. And a little bit also considering the theme of this event, we really wanted to go beyond the use of chatbot. And when we think about large language model, the idea is obviously taking consideration the code generation capabilities in particular, and looking at the TinyML perspective, some of the essential stage of its life cycle. One essential aspect also, and this was also briefly discussed in the previous discussion, something that we really don't want to forget is the cost, the actual cost from time and monetary perspective that the usage of API, large language models API, can eventually occur. And we have been trying to put in relation to the development of our framework. And the reason why we wanted to focus on the kind of the comparison between the traditional machine learning lifecycle and the tiny machine learning lifecycle is because this latter one include obviously some additional stage that it depends. It's to some extent a little bit more complex than the traditional machine learning lifecycle, and also it involves the hardware perspective, the constraint of the hardware especially, which is also reflected on the software, and so on and so forth. And as I mentioned earlier, the main idea was trying to understand what are the different trade-offs from different point of view when considering this intersection between the TinyML lifecycle and the usage of large language models for automating it. So essentially what we wanted to trying to answer with this kind of work are essentially three main questions. Obviously, to some extent, because we are kind of at the early stage of the prototyping and the work, the research work that we are trying to do, but the main question are essentially like the wish to understand what kind of stage, what type of stages of the TinyML life cycle can actually be automated using large language models. But also, more interestingly, perhaps is trying to understand what are the key elements of the large language models. Here I'm referring, and we will see shortly, for example, the prompt templates, the prompting of the model itself for tailoring and optimizing this automation. And of course, like as a kind of takeaway of this first two questions, trying to understand what are the possible bottlenecks, the trade-off, the challenges, but also the opportunities. And yeah, here there is some issue with the slides. But there is essentially there's supposed to be the framework slide. Is there a way I can get the slide in its entirety? Yeah, maybe. All right, but yes, I can. Yeah, essentially, there is like the key part of the talk, but for some reason it got deleted from the slides. Perhaps I can shortly trying to upload a PDF if it's possible. Perhaps this can help. But yeah, essentially, I will try to moving forward, and then perhaps we can get back to show the main components of the framework. But there are in practice three main aspects here. There is of course like a few aspects that are kind of in the surroundings of the framework. So I will get back to this, which is the human in the loop, the kind of input that we get from the whoever the user that is kind of interfacing the framework that we have developed. And there is also obviously the large language model that is in this particular case GPT-4o. At the end device, we will see that in our prototype we have been using an Arduino. And obviously the output, which is essentially including different artifacts like the Arduino sketch, the data process, and so on and so forth. The main component of our framework are obviously the machine learning software libraries, and I won't spend much time here for explaining what is this about. But the other two main components here are the large language model supporting tools like LangChain and LangSmith. Those are essentially two different frameworks that help somehow to interact with the large language model, in this case GPT, the API of GPT, but also very important the type of monitoring that is possible to do with these sort of tools for the debugging, testing, and also monitoring the key metrics that reflect the usage of large language models. And last but not least, very important aspect here is the prompt templates. So essentially what is injected in the large language model as input in order to get the wished and desired output. I would like now to spend some time. Perhaps actually there is chance to see now. I was able to upload. Here's likely the framework. I've essentially I went through this, but this can give a better overview. I guess the slides will be shared. But just to remark these three main components that characterize the framework, and as mentioned earlier, the 4 kind of surrounding, supporting aspect of the framework: the human in the loop, the large language model, the end device, and then whatever is the outcome of this processing. And I would like to spend some time on the third component that I've been mentioning, that is the prompt template. And these are essentially the structure that is used to, as I mentioned, to guide a large language model to produce the desired output. And here there is, of course, a lot of momentum and activities from R&D point of view on trying to understand what's the best technique to be used for this kind of engineering aspect of the large language model. In our particular case, I have to be honest, we have been essentially learning, just learning by doing and trying different approaches and trying to find the most suitable. Of course, there might be some further optimization that can be done. This is also part of our future work. But one of the lessons learned here is one essential part is trying to make the format and the structure of the prompt very precise in order to kind of have a consistency and accuracy. And it's well known, and this was also proved in our case, that the structured output like a JSON helped to get better outcome from the processing, and also different techniques like delimiters or indicators, and we will see shortly an example, can help the large language model to produce a better output. And in our particular case, we decided to structure the prompt in a way that we can essentially define in a modular way the context. So trying to explain the large language model the role and the kind of expertise that should use for producing the wished output. And then there is quite important trying to describe as much as possible the particular task that is going to perform. Referring to the life cycle management of TinyML, could be the model conversion, the generation of the sketch for the Arduino, and so on and so forth. Obviously, the error handling is part of the prompt template as well, and you will see shortly in the demo that this is very important, because it kind of allows the large language model to iterate over itself together with the framework in order to fix possible errors, and then a specification that essentially give additional guidelines to the large language model, essentially some background context, additional information that can help the model to produce a better output. And this is an example, practical example of what I just mentioned. Here in this case, this is the prompt template script for the sketch generation in the Arduino. You can see the context, the task. In the context, you're essentially telling to the large language model that you're an expert in tiny machine learning, etc., etc. While in the task is obviously more technical and oriented, and also perhaps trying to involve other components, either of the framework or the life cycle, for example, like the data set or other component of the framework. This is just an example. There is it's quite long code here. There is obviously very important the error handling that plays a key role in this context. And the current proof of concept involve 3 main aspects of the life cycle: the data processing. But the main emphasis that I'll try to give today during the talk is actually on the sketch generation. But we have also worked on the model conversion, which is obviously very important and key in this particular case, because we need to build our machine learning model in such a way that it can be executed in this particular case in an Arduino board. And the test case and the demo that we are gonna see shortly refer to CNN-based vision model. So we tested the automation with this very simple machine learning model of fruit with fruit identification using Arduino and TensorFlow. And before showing the demo, I would like to quickly go through the explanation of what is actually in practice happening in the life cycle. So we have obviously the user input, but this is of course like only at the first stage. Then everything is automated through the framework and the large language model. But essentially, what is happening, and that's the content of the demo shortly, is that once that the input from the user is acquired, the framework will try to cooperate with the large language model in order to, using all the background information in order to generate the code, the compiled code to be used in the device. Essentially, that's the final outcome that we are wishing to see. So here it comes now, the demo. I actually ask if it's possible to switch to the PowerPoint once again, because otherwise I guess we will be able to watch the video. All right, if it's possible, obviously. Okay, seems that it's not possible to run the video here, not even with the PowerPoint. All right, but yeah, perhaps I will keep pointer. There is a pointer, some pointer at the end of the presentation, and you can actually we will be uploaded, and you will get a chance to look at the demo itself. Yeah, perhaps it can be shown at some point. But anyway, I will move forward. I don't want to run out of time, but one key aspect that we wanted to understand also is the cost of automating the lifecycle management of TinyML via large language model. And one interesting aspect here is that the data that I'm going to present tend to essentially change over time, in the sense that the models, the closed source model like the OpenAI ones, are drastically changed, probably weekly, if not daily. So it's kind of hard to get reproducibility of these results, but there is pretty much consistency in what we have been able to observe from our analysis. And the type of cost that we wanted to analyze, it sort of includes the perspective both of the token and the time. So the token is this essentially unit of text that the model process. And what is important to clarify is that both the input token, so all the context and this kind of context, the error handling, the task itself, description of the task, of course, affect both the processing time, the monitoring cost, and also the computational resources used on the other end from the model point of view. And what is you can observe here is essentially a distribution of time and token consumption for the different tasks, for the model conversion, the data processing, and the sketch generation. What you can immediately notice both from the graph on the left-hand side, but as well from the table on the right, is that the success rate, and this was limited, the number of attempts for kind of querying the large language model was limited to 5 in this particular case. So you don't keep invoking the large language model endlessly. Was quite good, the success rate for the data processing and the model quantization and conversion. But you can see also that the sketch generation, which is quite relevant, right, for the lifecycle management, in this particular case, was actually pretty low. And this was also reflected to some extent on the average time and number of tokens that were kind of used for generating that output. Just to give an example, in the case of even past compilation, the sketch generation was lasting almost 2 minutes, and the number of tokens was not as high as the data processing, but fairly high. And here it comes one interesting perspective here, which is the total cost on average for automating and deploying this kind of different steps in automated way. And obviously, this doesn't look much if we look at the actual cost in this case. For example, for the sketch generation, it's like a 14 cent dollar. Is not much in the worst case, but obviously we need to take in consideration that this could potentially be on a very high scale. You might need to manage a bunch of devices, and you might have a much more complex model. So to automate, so on high scale, this can become a relevant bottleneck. So approaching the conclusion, trying to answer to this question. Of course, it's not a definite answer. There is a lot of work to be done, but the reality is that there is some potential of using a large language model for automating the TinyML workflow, especially for some of the stages that we have been analyzing, like data processing and model conversion. But there are still quite many challenges. For example, key stage like the sketch generation proved to be a big bottleneck, and also our proof of concept is essentially limited to a simple model, one type of board. So obviously the complexity can become much bigger, and so the average time and all the different trade-offs that we have been considering. And here it comes the opportunity, right? There is, of course, opportunity from the perspective of first trying to support the large language model with the external tools, and there is a lot of work ongoing in this respect, but also kind of trying to augment the knowledge of the large language model for trying to optimize and get more qualified and efficient output. But last but not least, and somehow this kind of connects to, I guess, what we are going to see in later today and tomorrow, connected to the fact that we really do believe that a key role will be played also by the end device themselves, whether they are very constrained like Arduino, where of course there won't be the possibility to run small language model, or something a little bit more powerful like single board computer. We really believe that the device can become a key essential part in somehow becoming the external tool, the self-external tool involved for optimizing the life cycle, because you can essentially abstract device-specific information, application-specific information that can reduce the cost and the amount of time required for processing the life cycle stage at the large language model side. And soon to be published overview about this work. We will make sure to add also a link to the demo, perhaps sooner. But this is pretty much concluding my work, and I would like to thank Han, especially that from the University of Helsinki, who has put the theory in practice in this work. Thanks a lot.
Thanks, Roberto, for your presentation. Really appreciated the. We have still some time for a few questions. I have some, Roberto.
Sure.
In the life cycle, what are the technologies which are trickier or more complex to deal with, especially if you want to generalize the workflow on different tiny target hardware?
Yeah, as I mentioned in one of my slide, the kind of illusion here comes from and we can definitely say that this work generalize over different type of models, because it's quite complex. Definitely, what we have been observing and we have been testing largely with different configuration, even with a very simple model like the one that we have been using for our prototyping, the sketch generation, that perhaps in this particular context of TinyML devices, along with the model conversion, represented the key part, right? If you are not able to generate correctly the Arduino sketch, it's pretty much useless what you're asking to do, right? So definitely that part is still quite challenging. Obviously, there is it's been proved that the code generation capabilities on for example, languages like C, C++ are less performing than the code generated, for example, for Python. So that could be one possible reason that it's kind of worth to investigate. But definitely, the sketch generation in this particular case was the main bottleneck, and expect to be even a little bit more complex if we take in consideration a more complex model, for example, or different type of devices. So definitely that was the trickiest part.
For example, also considering hardware with neural processing unit embedded, is that true as well?
Yeah, at this stage, one of the one wish that we have next is trying to look at devices like single board computer that have this AI acceleration capabilities, whether it's GPU or TPU. But it would be definitely interesting to look at those devices as well, because in that particular case, I expect also the model conversion to become a possible bottleneck, because there are additional requirements in terms of libraries that definitely can make the data processing a little bit more complex. We saw a quite fair success rate. It was pretty much 90% with the model conversion. But I expect in the moment that we are going to use devices with AI accelerator, embedding AI accelerator, also the kind of success rate for those particular stage could actually go down. And that's the reason why we truly believe that the kind of possible cooperation, or anyway the usage of either a small language model on edge device, on this type of devices, of abstracting in a smart way the information from the end devices, can make this sort of use a little bit more effective, and also from additional perspective like privacy, etc.
And maybe one last question, which somehow is inspired also to a question I see in the comment, between the comments. How often should I reapply to the workflow in the real life, in your opinion? Are there conditions to be set or to be respected? Any consideration on that?
Well, essentially, it really depends at the end of the day how often you wish to update your model, right? I guess that's the main thing that drives the decision on how often you would like to involve the large language model for automating and updating. I guess it depends on the application. So in the moment that you have like a big data drift and you really need to upload and retrain and convert the model more often, those kind of application will certainly require a larger employment of this type of automation. Otherwise, if it's very simple application like the one we have been showing, for example, today, in that particular case, perhaps I don't see like urgent need to recursively recurring on this type of solution. But there might be cases in which this could actually be the case. I'm thinking, for example, sort of time series forecasting models where you really, in specific industrial setting where you need to update the model more frequently. So those particular cases, I do see a kind of increasing need of automation and iteration over the stage.
Thanks a lot, Roberto. There are also further consideration
Absolutely.
because your presentation and the content was really interesting and suggesting also further question. But we needed to stop here. Thanks a lot for your contribution. It was much appreciated.
Thanks a lot for the opportunity. Thank you so much.
You're welcome, Roberto. Thanks to contribute. And now, I kindly ask Chen Lai, hi, nice to meet you, to show up. And Chen is going to speak about unify and fast deploying GenAI on edge with ExecuTorch. The floor is yours, Chen.
Great, thank you. Hi, everyone. My name is Chen, and I'm from PyTorch Edge team at Meta. So my talk today is about fast and unified deploying GenAI on edge with ExecuTorch. As we know, PyTorch has become the unified framework for working with ML models. Most researchers start from PyTorch, train with PyTorch, and deploy with PyTorch on server side. However, deploying models on edge is just more difficult because of challenges like constrained memory, compute, and heterogeneity of hardware devices. This often leads to fragmented ad hoc solutions. So, can we apply a unified edge frameworks to generated AI systems while remaining performant? ExecuTorch is our answer, and I will introduce a bit. I will introduce it in a bit shortly. So let's take a step back and see why people are interested in running ML models on edge. Well, there has been an emergence of running AI models on devices, including mobile, biosensors, IoT, etc., because of listed opportunities like low latency, privacy, etc. However, there are definitely challenges. So edge devices usually has like lower battery life, less memory, and most of them also has thermal requirements. The diversity of the hardwares are also just much more broader than server space. Here, I would like to introduce ExecuTorch. It's a fast and unified solution. ExecuTorch is the solution from PyTorch. To run PyTorch models on edge devices, we aim to support iOS, Android, and embedded device. It's fully open source, and we are working with Apple, ARM, Qualcomm, and MediaTek to support their hardwares to achieve the most optimum performance. ExecuTorch starts from PyTorch model, run through torch.export to get a graph. After compilation and transformation, it will generate the ExecuTorch program. On edge devices, the runtime will load the program and execute the instruction. So this is pretty much the ExecuTorch workflow. And here is the example to run Llama 3.1 A-billion on Android devices. And the QR code can be used to try it out. We also support multimodality. We support running Llama 1.57 billion on Android. For some reason, like it should be a GIF image, but it's not playing. But yeah, I think it's like in the QR code we can see the same demo there. Why do we want to use ExecuTorch? PyTorch empowers AI researchers already nowadays, but the path to deploy the model on edge is just really fragmented and complicated. We would like to support it in a principled way. For example, we want to leverage hardware accelerators for optimum performance, and user can easily follow the similar workflow to target the different devices. Our runtime can also our runtime can target most devices, and we don't need conversion anymore. So here is the XTorch timeline. We went through preview on October 2023, and we announced alpha on April this year, and we have our beta released last month on PyTorch conference. The official release for beta is this week, so it will include the performance llama examples, and in the 2025 we will add more richer ecosystem integration and robustness. For beta, what is new? We aim to target stability, performance, and coverage, especially on stability. We target on API stability and also backward forward compatibility. On performance side, we focus on optimum performance on GenAI, for example, Llama 3 AB and then Llama 1.57 billion. Of course, we also support the latest Llama 3.2, 1 billion and 3 billion models. And on the coverage side, we enable more kernels, and we focus on set up the benchmark infra and also the on-device debugging and profiling infra. Here, for the stable APIs, we set up the life cycle from experimental to deprecation, such that like when user integrate to the latest code, it won't break their existing integration code. That's what one of the most important parts for our beta release. Here, I'm going to walk through the GenAI, the on-device GenAI use cases. CPU is a crucial role especially when we want to enable a wide variety of PyTorch models on XTorch and experimenting novel research ideas like Llama quantization or LLM quantization. Right now, we can run family of LLM models and a wide range of other LLMs out of box for GenAI use cases. Our primary focus for our CPU performance optimization has been the ARM CPUs. We developed Gen kernels for Omnion to achieve peak CPU tokens per second on a variety of edge devices like Android and iOS phones, and also Raspberry Pi 5. Collaborating with Google, the new 4-bit Gen kernels are upstream to XMPAC, and working together with ARM, we also feature faster CPU prefill performance through Collide, which now has similar 4-bit Gen kernels. CPU is our baseline. In addition to CPU, a critical puzzle piece of on-device AI is the neural processing units, as known as NPU. It has more TOPS, which means faster prefill, and it is also more power efficient, which is crucial for battery life. Most software frameworks may not have the capability to efficiently enable NPUs, or the stack can be kind of fragmented. So we create a delegate API in XTorch. NPU can be accessed by delegating part or the full PyTorch program to the corresponding backend. So we collaborated with Apple, MediaTek, Qualcomm, etc., to integrate XTorch into their development flows. Note that although NPU power is leveraged, we don't move away from PyTorch and XTorch ecosystem. It keeps consistency when compiling the PyTorch program from server to device and help users to profile and debug on device. Now, as I mentioned, Llama 2, 3, and 3.1 and other LLMs can run on phones through these accelerators. We also support multimodals. Here's the examples to run Lava models with both image and text inputs. The image encoder has 307 million parameters with 8-bit quantization. The text models has 7 billion parameters with 4-bit quantization. We provide AOT and runner components with CPU optimization. And the QR code is the instruction to try it out. We are also going to support other modality like audio, video, and yeah. So to support GenAI use cases, above a number of techniques are used. So here we list some of them, like 4-bit, 8-bit for llama models. And to further improve the post-training quantization accuracy, we also integrated the new spin quant technology. We are also actively working on like the other new technology like long context length, lower bit quantization, and parallel decoding. So yeah, so here is like for the on-device, like it's a sort of a short summary for the on-device LLM status. So on CPU, we have the optimum kernels. On accelerators, we work with our partners to lower LLMs running on the backends, including CoreML, Metal, Qualcomm, and MediaTek. So right now, they are all enabled, and then the LLMs can fully run on these accelerators. This is like taking a closer look at like what is needed, what is the fundamental features needed to enable LLMs on edge. So quantization like LLM, large language model, meaning the weight is large. So the first optimization we always do is quantization to compress the model size. Secondly, we need to optimize the memory. The bandwidth among different memory regions are just really different, and we need to plan them carefully, especially when we are memory bound. Decoding accelerations. So users just want to get the result right away when they type the prompt. Fine-tuning, we would like to fine-tune different LoRa adapters for different tasks, like summarization and writing emails. DevTools, it's a pain to debug accuracy and profile. And that's Xtorch advantage. We provide native tools. And like, here's the example, like say, for example, when there's a prompt saying like, how is the weather? And then if the LLM start hallucinating, then it's really hard to debug, especially it's on device. So with our partners, we can help you to debug, even if it's inside of the black box accelerators. So here is like more concretely, like what is the exact techniques here? For quantization, there's like 4-bit linear kernel, KV cache quantization. For memory, like one example is like have KV cache state. And then we can also do cache application. For decoding acceleration, we can do batch refill, and we can also do speculative decoding. Fine-tuning, as I said, like LoRa is quite common. And DevTools, that usually comes with profiler and also accuracy analysis. There are 2 more updates. In addition to GenAI support, we also enable OSS reproducible performance benchmarking infra, either like on-demand benchmark request, or we can also schedule benchmarking to monitor the performance trends. They will go through the GitHub actions, and then the benchmark will run on AWS device farm to generate the performance matrix. We are also working on these experimental features on device training and fine-tuning. By design, it's composable with the existing Xtorch flows and backends. On the right-hand side, we show a convergence of loss when fine-tuning LoRa 5.3 models. Since it's a proof of concept, there's still lots of ongoing work and feature planned. Yeah, check out our repo. Ecosystem and community adoptions. So Xtorch does not work alone. It starts from torch.export, where the compute graph is captured with dynamism. Quantization is supported by Torch.io, where the lower bits quantization kernels quantization API will be hosted. We built this LLM vertical stack with Torch Chat to showcase LLM inference on mobile devices. TorchChat is a PyTorch library showcase how to run LLMs across laptop, desktop, and mobile. For model sources, the model can be fine-tuned models from Torch team with PyTorch native support. We also partner with Hugging Face as well to make the models XTorch compatible, like Gemma 2B and 5 Mini. XTorch ecosystem is built with all the parts working together. Even though XTorch just came to beta, we have seen active adoptions. It has been adopted by Meta products. So XTorch support Ray-Ban Meta smart glasses, Oculus Quest 3, and Meta apps like Instagram and WhatsApp. It has been used by developers in the community. So example including like in painting mobile apps from Software Mansion. It's based on Efficient SAM and Swing Transformer and use CoreML Delegate for acceleration. XTorch is used in the inventory mobile apps like Diksha, running CV and OCR models for medical devices. We see researchers are adopting XTorch as well, example including mobile LLM, AQLM enablement, Windows enablement, etc. So coming back to the first slide, we provide XTorch as a PyTorch platform to help deploy LLMs and many others to edge devices. It will be like this week. It will be the formal beta status. Yeah, you're welcome to visit our GitHub repo and try it out. Yeah, so that is pretty much my talk, and I'm happy to take questions if there's any.
Thanks a lot, Chen. It was really a great talk and rich of many information. There are questions from the community. Let me go through some of them. Chan Seok is asking, for example, if there are hardware dependencies for the XQ-Torch model inference.
So it depends. Well, I think XTorch itself is targeting on like portability, meaning like the XTorch runtime. It can run like on pretty much everywhere. And now when we talk about like running XTorch model for inference, say for example, then like usually user will have some hardware on top of their mind. Like if user want to target iOS, that's totally works. And if user want to target Android, that will works. And if user want to target Raspberry Pi, then that will all works as well. But for the XTorch runtime, it doesn't really have it's designed to be portable. Like it's supposed to run anywhere.
Okay, and let me complement this question with maybe a comment. How would you consider easy or hard the interface of XQ-Torch to custom-made NPUs? You know, is there a fair amount of work to be done? Maybe some of these NPU, sorry to interrupt you, maybe some of these NPU in the future will feature also ad hoc accelerators, optimized memories, maybe in-memory computing, you know. Any comment in this direction?
Oh, that is a very good question. And it also like part of the topic here. So the goal for XTorch is make it easy to use for users. And it's aimed to like both unified and also aim to fast. I agree that like, say, for example, the NPU can have like a dedicated path to like further like to make it really specialized and then performant. However, like, for example, if I'm just a ML researcher and I may not know that much about this specific NPU, and I need lots of background knowledge such that I can deploy my models on the NPU, and I may need to follow a different instruction. so there's like lots of burden there, and the path can be really fragmented. So for XTorch, our goal is like it's a unified way. So if I'm researchers and the line of code to target, say, Apple's NPU or versus like Qualcomm's NPU or like MediaTek's NPU, the flow is pretty much the same. So user doesn't need to like really look into like how this specific NPU can work. That's like I think the advantage of XTorch. So we hope like it's pretty much like user doesn't really need to like know all the details for this NPU, but they can just run it and then it will just work.
So it means, thanks, Chen. It means that it's abstracted enough such that I don't need to be a super expert of the hardware underlying, because it would require much investment in knowledge. Right?
Yeah, that's expectation. And with the default path, we also aim to like have the best performance as well. So yeah, as I said, like we wanted to like provide users a unified way. Like essentially the flow is unified, but it's also like performant.
Thanks a lot. Let me go through some other questions. For example, from Davis, you spoke about 4 bits, but Davis is asking if there is or will be support for FP16 or other formats, mixed precision. Mixed precision can be a great configuration for generative models at the edge.
That is an excellent question. So yes, XTorch supports FP16. And for the hardwares, for the NPU, as long as they support FP16, then it will just work. Say, for example, if once NPU, they support FP16, it will just work out of box. Regarding the other lower bits or mixed precision, yes, they are supported as well. We are bringing up a list of lower bits kernels, like including 2-bit, 3 bits, all the way to 6-bit or 7. I think it's up to 6-bit. I'm not sure about 7-bit, but we support a list of lower bit kernels, and then it's up. It's like it can be used. And then like for the mixed precision, yeah, so I think that's part of like our quantization framework. We support custom annotation, and then essentially like user can decide like how I would like to quantize my input, activation, and weight, etc. I understand like mixed precision is actually very important, especially for LLMs. Well, I guess maybe it's important for other models as well, but like for mixed precision, yeah, in short, it's supported.
Thank you. And staying a bit on the quantization topic, there is a question from Chan Seok about QAT, quantization aware training. What's the kind of support you have?
Yeah, it's supported. So for the our default backend is the CPU backend, and it supports QAT. And pretty much every backend has their own quantizer. And yeah, so I think I think currently the CPU support XTorch itself support QAT, and then whether or not this backend can support QAT is based on the backend's implementation. I think currently Qualcomm is also investigating QAT as well. Like I think it will be up very shortly.
Thank you so much. There are also other execution models out of there. So, for example, Javen is asking about TVM. Any comparison? I would generalize also to, I don't know, any other interpreter that you may have already considered.
I see. Yeah, that's also good questions. I think TVM is probably like a different ways. I think XUtorch, I guess like I'm not quite sure the latest status for the TVM. So, but I can tell like one advantage from XUtorch compared to other framework is that it's leveraging the latest torch.door export. And then the benefits of like, I think there are mostly two benefits. One benefit's like it carries over like all the information from the PyTorch source code all the way to the on-device runtime. Like meaning like, say for example, if I have a PyTorch model and I author it on server, and then like somehow like it's just error out inside a NPU. And via other framework, it could be kind of tricky to figure out how to find out where it goes wrong. But like via XUtorch, we have the native support, and we can help you to find out like where, like say for example, why it's slow, and then also like which line might be wrong. We can help you to find out the exact PyTorch line of code in the source code. Yeah, essentially like easy to use as probably like one of the thing out of my mind. But I guess like they both have their own, but they like TVM might have their own advantage. I probably don't have enough knowledge for like for this comparison here.
That's fine. And another question maybe is obvious for you. Anis is asking if Llama, the Meta Llama, has XUtorch support now.
Yeah. So like all the, well, I guess like for the smaller version, like Llama, for the XUtorch, we support Llama 2.7b. We support Llama 3ab, 3.1ab, 3.2, 1b and 3b models. So yeah, pretty much like all the models that can fit to the to the RAM, then we can run it.
And another question from Nick: what are the memory footprint requirements from Llama 3 8-bit? Let me also add, in general, any comment you may share about the capabilities of XUtorch to deal with the memory system of the target in order to optimize its usage.
Wait, so I guess like the question asked here is the memory footprint requirements for the Llama 3AB, and what is your part again?
And if you, after you answered this question, maybe if you can comment about the capability of optimize the memory usage of the target from XUtorch point of view. You know, embedded system has a lot of constraints in terms of hardware, in terms of embedded memory.
I see. Yeah, that's actually a very good question. I think for the footprint, I think in the GIF we actually have it. I don't have the exact number, but what I can say is like the memory weight, the model size in total is around is less than 4 gigabytes, and because like we can run it on iOS. And for the iOS, the app will be queued if it's over 6 gigabytes. So I believe it's less than 6 gigabytes. We did some profiling before for the memory footprint. I just don't quite remember the exact numbers. Here's I can also like briefly mention like essentially like how the memory planning works here. So for the memory footprint, we actually have the toolings to figure out like how much memory is needed when we just export a model. Because like it's pretty much like it will be just have the model weights that is like constant memory, and that's like less than 4 gigabytes. And then we have the and then also for regarding how memory works in XGTorch, the way it works is like we pre-allocate a chunk of memories, and then we will plan them carefully such that we can reuse some memories like when this tensor is no longer needed. So we actually have the tools to find out like how much memory is needed there. Yeah, I hope. And then like based on the tooling, we can figure out like we can continue optimizing it.
Thank you so much, Chen. I encourage you to share more numbers later on if you have time on the comment sessions, because people are really interested. And I think I can also say the XecuTorch investments and the impact on the community is really interesting. It's incredible how Meta is investing on the edge. That's fantastic. And thanks a lot for your time, Chen, and to have accepted to stay with us and to present XecuTorch, and for the passion to reply to many comments, and there would be many other in the future, I'm sure. So thanks a lot for your time and a great talk.
Yeah, I will leave the answer, like I will continue answer the question when I go there. Thank you.
Sure, thank you, Chen. And now it's time for ELOC presentation titled Bringing Small Language Models on Edge, Learning and Challenges from Automotive Domain. The floor is yours.
Thank you, Danilo. Good morning, everyone. Happy to be part of this event. First of all, thank you, TinyML Foundation, for having this unique conference. Thanks to all the organizing committee members for this opportunity. So I work with BOSCH India, and we do research around AGI and TinyML for both mobility and non-mobility domain. So this work is a joint collaboration with my colleagues Ashutosh and Guru Prasad. And what I'm going to talk today is that how you can leverage, the SLMs to address the domain-specific problem statement. And while we address, the problem space for such a enterprise side, what kind of the performance we can see from the real-time deployment from the edge device, and what are the certain challenges we faced as part of this problem space solution. So now let us understand what are the current motivations for talking about the SLM, and how SLM is helpful to unlock new value proposition. We have seen, the lot of buzz and then use cases around generative AI or the larger LLMs. The size are also getting increased. But when it comes to the customization and we want to solve it for, any specific smaller data set or domain specific data set, we have seen the performance concerns. We really don't have a control how you are going to process the information, whether the performance will be reliable enough so that you take certain decisions or offer the new solutions for the customer or the end users. So with SLM we will be having a lot of the customization support. Another critical aspect from the community side is that we really don't have the infra available when we want to run the generic LLMs. And when it comes to the running those LLMs on the edge, again it's very challenging, not in terms of say the cost, but in terms of your energy for energy consumption for the inferences, and from the sustainability point of view. This is more critical again for the automotive domain, because in automotive domain, when you want to get it integrated on the vehicular edge, we really don't have that much of compute infra what we typically see in the data centers, right? So this is where when we have the dedicated or the smaller task, I truly believe that SLM will be going to play a major role, and we can offer and then do a lot of the interesting solutions around SLM. In terms of performance, there is no doubt that when we are going to deal with the domain specific data set, performance compared to the generic LLMs will be better. And the same I am also going to demonstrate through one of the video what we will be seeing. Now, from the user's perspective, privacy and then the different, the regulations around privacy and data security is a concern. Now, in the typical current scenario, we have solutions which are currently hosted on the cloud or the centralized server, but the users are not really keen to adopt such products where your sensitive data and then the private data is concerned. With the help of SLM, it is possible to address some of the the problem space in the privacy, and then bringing more trust in your product offerings and then the solution what you are going to have. So this is another the driving factor around SLM. And in terms of your market size, this is one of the report in 2024 published, which talks about the market growth is also very interesting. And then we will be seeing a lot of the solutions which will be coming for different industry verticals, not only to the automotive but the different industry verticals also. So with this the background, I would like to now uh, focus on how, say, the automotive domain will be going to leverage the SLM and the larger LLM, which will be coexisting together. And then this is where we see the new age AI architecture which is going to be adopted in the automotive domain. We will be seeing the scenarios where you have solutions which are currently deployed on your vehicular edge, where we will be having personalized SLM to address your domain specific task, multimodal SLM to understand your different data inputs. We also envision where getting, say, the mixture of experts integrated on vehicular edge will be playing a crucial role. And the way solution is going to come when you have the connected and automated vehicles on road. We are not going to just have the SLM which will be just focused around the customized or a smaller task. But when it comes to dealing with some of the compute heavy task, the complex task, again we have to go to the centralized architecture. This is where the interplay between the SLM and cloud hosted centralized services will be coming very handy, where we will be having opportunity to deal with all sort of different data, be it your image, text, lidar, radar, whatever it is. In fact, we have seen most recent work which are published in 2024 talking about leveraging generative AI to understand the capability for the technology like the B2X, where vehicle will be exchanging a lot of data to the infrastructure. Right now, the critical question from the automotive domain side is that when we envision SLM to be integrated on the vehicular edge and interplay with the cloud-centric architecture, what kind of the use cases we want to execute on the vehicle itself, and then what we want to offload to the cloud. So this is where the future around and then the solution perspective around this SLM and then the having said the centralized LLM hosted on the cloud will be very critical. In addition, since you will be driving, say, the vehicles will be on the road, it is not always true to the hold your data which are always seen or as part of the training data. We will be also seeing the challenges around situational events, which are more dynamic in nature. Right now, when you have such kind of dynamic data in place, it is very challenging to use those data, use those information to the vehicular edge itself, where the SLM will not be working. And in this case, we really understand that situational events will be very much helpful when we want to get it deployed on the centralized architecture or the cloud native solution. So now let me share the problem statement what we are solving. So consider a scenario, since the connected features inside a car is getting increased day by day. We are seeing a lot of solutions talking about when you have, say, the connectivity and the stable network. you can access all those sort of integrated features. The vehicles are getting more feature rich. But what happens when say someone is driving and then you don't have the stable network connectivity, right? You really don't have, or let's say when you are driving from point A to point B, you will be having say the intermittent network availability, the bandwidth which need to be there to, let's say, deal with your audio input, or dealing with your images, will not be sufficient enough to serve the solutions which need to be consumed by the driver or the user itself who is driving, right? In addition, we also want to digitalize the owner manual, where you can have a control while you are driving to understand the different warranty policy or the operational and maintenance side of it, right? So with the help of SLM, it is possible to offer you the offline services, and the users will be benefited. They don't have to really bother, because we really don't want to just force a smaller task where, let's say, if I'm just trying to understand how to go and operate in the eco mode, how to open, if I'm just trying to understand having say the 360-degree camera configuration, which may not be very much familiar to me, but I just want to configure as per my requirement. Now, having such kind of request from the user while you don't have the stable network, it is going to be very unpleasing experience for the user. But when we have solutions around SLM, where we have integrated solutions on the SLM, and then get it deployed on the automotive grade hardware, it is possible to solve those kind of the scenarios. Then in scenario two, again we envision that SLM, to enable the offline services, it is possible to get it deployed on your mobile phone. And just imagine that you are stuck where your vehicle is breakdown and you need certain support. You may be just clicking a photograph and trying to understand what may go wrong. How can I fix it? When I say fix it, it's not from say the service guy side of it, but it's just trying to understand what went wrong. And possibly you can also try to get the contact information of the nearby your the service operators or the service dealers, those who are available there only, right? So that's the scenario two. Could you please go back? And in scenario three, we want to, enhance the in-vehicle experiences, where the small agents are possible to get it integrated on the vehicle. Imagine a scenario, let's say when you are driving on road and one of the glass window is open, right? Your AC is turned on. So you can get input from your Gen AI agent, which is possible to get it integrated on your vehicle, saying that the window is open and AC is on. Do you want me to close the window? You can do that. So such kind of, the small solutions which we will be seeing in the connected vehicles ecosystem will be possible to get it developed in using say the SLM. Now for today's talk, what we will be seeing as part of demonstration also is that we have done say the scenario one and scenario two, which are currently hosted on the edge device. The scenario three is work in progress, which we are hoping to get it completed in the coming months, and then probably we discuss on those lines also. So quickly about bringing, the making your owner manual digitalization. So these are just say the number point of view, so how the data looks like. We will be having both, the structured and unstructured data when we are dealing with the PDF file. So what we have done fine tuning on the Tiny Llama 1.1 billion chat. We wanted to develop this conversational agent. We have processed this information, we extracted this information, but right now in the current demonstration, what you will be seeing, we don't have, the extraction done or understanding around the image, and then what are the text embedded on those images. So that we have not done in this work, but this is possible where we can make it more mature now. So the scenario where you want to do it, a lot of configuration to understand and all is possible, and then we will be seeing the same. So Tiny Llama 1.1 is used here, where we have used the base model. we have done the fine tuning on our server machine, and once that is done, we have optimized. We have followed, the post training quantization approach, where we converted it to the first 8-bit to understand the performance, and then the 4-bit scenario. Can we go next? Yeah. So this is benchmarking results. We have done a lot of benchmarking, not only to the fine-tuned model. I don't know if you can see here the green one. We have leveraged, the base model, which was having a size of 2.2 GB. Right? We deployed this huge case around both your CPU and GPU architecture, considering Pi 4B, Pi 5, and Jetson Orin Nano. So Jetson Orin Nano, if you see here, 8-bit, it was the maximum throughput what we have received is 26 token per second, and then the model size is 1.2 GB. But for the 4-bit, we have trimmed it down to 637 MB, and the maximum throughput what we have received on an average is 40 token per second, right? So in terms of model size optimization, we have done it 71.8 percentile. The throughput is improved by 8x, and if you are going to convert it in the percentage, it's somewhere around 700%. The throughput improvement. The average load time of the model is just 1 second. And along with Tiny Llama 1.1, we have also tried deploying, the Mistral 7B, where we recorded the performance for 4-bit for 9 token per second. Tiny Llama 27 billion we have also deployed on the edge, and we recorded throughput around 8 token per second. So right now, whatever the responses we have seen, it's much faster to address the problem what we are going to have. So in our solution, we have integrated both your chat along with your audio input, where you can get the interaction done through your audio, and then text to speech and speech to text is also integrated as part of the solution. So this is about the benchmarking what was done. Now I will be playing the video if I can do that. Yeah. So can you see my screen? Can someone confirm? I'm just trying to play the video. No. Okay. So looks like it's played. Yeah. So here, if you see, you can see the performance real time deployed on Orin Nano. We have asked multiple questions, and you can observe how faster it is and how precise and concise answer it is giving when we have trained it on the custom data set for the owner manual. So this is one of the questions, and this is the settings where we have used it for 40 token and 4-bit optimization is done. Yes, similarly, we can see the better performance. What we have observed that when we have compared the results against your generic Tiny Llama 1.1 4-bit quantized one, we benchmarked, and then we have received accuracy around 93 percentile. We still find a scope to improve the performance further, because certain data are not processed in the right way, where the model, the SLM itself, is not giving you the proper answer. I would not say that it's completely wrong, but it's just giving you, say, the half-cooked answer, which are partially true and not always true all the time. So this is around your this the fine-tuned model. We would also like to show you the corner cases where it started failing, where the mix was when you are dealing with your say text, and when you have a combination of the numerical values. So this is where, let's say, when we are asking about the particular address, ideally the response should be that the response should be where it should be asking, the further question. For an example, when I'm asking the address of one of the OEM, the location, it is giving you the answer. It's not nothing like that. It's not giving you the answer. But ideally, let's say in a state, there could be the multiple service providers, and ideally the answer should be that which, the city or which location area you are interested to get that response. So we believe as part of our next step that we will be just, doing that data processing in the best way possible, so that we capture those corner cases what you are currently seeing here, where it is not giving you the proper answer. In addition, we have also asked, let's say in the car, how many sockets are available, USB sockets are available. There also it failed to answer, and the performance when it was done for both your, let's say, the base model as well as the optimized one for the generic one, it was really worse. But as part of, the performance is concerned, the SLM is outperforming for our domain specific problem statement, working real time with faster response time. So here, for an example, when you are asking about one of the question, it is saying that about the USB, it is saying just replace it one. And the same next question, when I am asking that how much current we can output we can get from the USB C socket, again it is not giving you the proper answer. So these are the certain corner cases what we have observed when we are solving this kind of, the problem statement in place. So I think this gives you the the real time feel when it is deployed, and how faster it is to run such, the solutions on the edge, and you can further leverage it for make it more robust where the corner cases are not there. So for an example, in your user manual you can have the multiple warning indicator, but when you are just asking about the orange indicator of the infotainment system, ideally it should be just asking, the what kind of, the symbols you are seeing, and then so, but it is just giving you the answer which it finds, more accurate for giving you the response. Another part where what we have observed that the context window is also very limited, where if we can expand it, because TinyLlama 1.1 is having very limited context window size. If we expand, we certainly want to do certain design of experiments around it, so that we understand the performance on the real time device, and understand how we want to further make it more accurate to bring the robustness in the solution in place. So with this, we'll switch back to the presentation. All right. So this we have covered, because we just wanted to. This we have already shown. Yeah, this is completed. All right. So from the automotive point of view, if you see, we really need support from the standardization side. What I mean here, let's say when you want to get it deployed, for the automotive domain, what kind of use cases, whether you want to realize the safety critical application, or the generic smaller task, right? And if we want to, let's say, also trying to understand, because people have been doing research around connected and autonomous vehicle to understand the new scene generation. Once you have the new scenes on road, do you want to take that decision on top of it? And if you want to, understand or taking the decision on top of it, what inferences you are getting from this kind of solutions, you really have to follow the standardized way. And this is where, as a community, we have to come together, we have to build more partnership, where we exchange, the knowledge, that what kind of use cases, what was the hardware used, how the data was processed, whether it was, done piloting done, or it was just done on the synthetic data. So this is where, especially for the automotive domain, standardization will be playing a major role to bring, the generative AI on the edge for the vehicular ecosystem. Now, whenever we have the new age technology in the market, it is also very critical that we, bring the trust in the among the users, right? Let's say already we have seen a lot of increasing concerns about data privacy for generative AI, as well as the AI products all around the world. But if we have the privacy by design when we are designing the new architecture for the SLM for getting integrated on the vehicle, we have to enable the user with that trust that, hey, this is the way your data is processed. We are not leveraging the data in this way. We are not sending the data on the centralized way. We are just doing all this the computation on the device which is not leaving your data. So how you bring that trust among the user is another concern from the automotive domain, where we need the efforts around building such architecture which covers those areas. Now we have seen also some of the reports where researchers identified that the performance of SLM are hardware dependent, right? Now if that's the case, where we say that the performance is hardware dependent, what if you have one of the premium segment of your vehicle, another could be just having say the less compute infra, right? Now when you have the same set of solutions deployed on the automotive side, are you going to have the similar performance, right? How we are going to do this kind of the benchmarking, where we understand where your solution or the SLM is going to be deployed from the automotive domain point of view, where we need not only on the design focus for your SLMs, but it's also for your optimization part on the inference, and then the further the other optimization where you have to deal with. Again, we truly believe that SLM and LLM will be interplaying each other. What kind of use cases we want to derive in the collaboration phase would be certainly need a lot of research efforts, where we need to have the experimental insights, and then the lot of discussions around what need to be offloaded on the cloud, what need to be just running on the edge, vehicular edge. And yeah, these are the key takeaways. What we have observed that SLMs are promising when it comes to the domain specific task. We have identified the scope that if you have the better data for the training, it is possible to address the corner cases as well. And future of the connected automotive experience will be just hybrid architecture. Standardization efforts just spoke right now. We also need fair benchmarking results, because most of the automotive domain solutions what we have seen, it's done on the closed data set, right? If we as a community, if we can come up with the openness in the data set through the community research, it is possible to address the certain open questions which might not be covered by the researchers who have done work around it. So just having the fair benchmarking results shared with the community will further play a major role for automotive domain when we want to get it realized for the automotive domain side. So with this, I will stop here, and I am happy to take questions. Danilo, you are on mute. I can't hear you. Yeah.
No, okay. Thanks a lot, Alok. It was really interesting, your presentation, because of not only the topic SLM, but also because it's coupled with the automotive domain. So thanks to clarify and expose the need of GenAI applied to the automotive context, starting with SLM. So there are a couple of questions before to close this part of the agenda. It's about, let me quickly find, it's from Chan Seok Kang. Is there any protection for hallucination while using in-vehicle SLM? I think is related to the safety aspect, which is super important in automotive. Any comment from your side, Alok?
Yeah, so we really believe that prompt engineering is going to play a major role, and we can also bring the let's say when you are getting the response from the SLM, you can bring the context part there, so that you can just have the continuous embedding to derive the relationship what you are going to share as an output. But ultimately it's a lot of the experiments. It would be very early to understand, but as I have mentioned, that if we want to go for, say, the safety critical applications, we really have to understand what kind of the decision you are going to take based on the inference which is coming out. But a lot of design experiments need to be done for the prompt engineering, and then bringing the context part. This is where we see potential to address the hallucination in SLM.
I also have a question for you, Alok. It's clear, and thanks to share your view about the use cases. So the digital manual, the digital assistant, these are super important. I see really a strong and a need about this kind of support in automotive vehicle. I think is also a matter of fast adoption. I hope it will be very soon adopted. What else? What's next? I mean, a digital assistant only on about understanding my questions and provide me answers so that I don't look at the manual, or anything more wider than this in your vision, in your future vision?
Yeah, so certainly I think from the future applications, we see potential around the Gen AI agent or smaller agents, which will be taking care of certain functionalities integrated in your vehicle. For an example, I had cited one example where your glass window is down and you are driving, right? So if you're driving, so it can be controlled through those SLM. But the larger vision where the OEMs are thinking about bringing the more empathetical scenario where you can interact with the conversational agent and then do lot of personalization where you solve it. Let's say if you are exposing your data and then you have the stable network connectivity, you can also go for the composing emails and then giving you the perception around what when you are, let's say, driving from parking yard, right? And once you have started, it can give you the surrounding information also. So such kind of emerging use cases people have started talking about, but it's still in the progression phase where we will be seeing the adoption around it. So again, I also believe that SLM is not going to be just be helping in what we have discussed today, right? It has to be where you are going to have cloud native LLMs also to bring more feature rich solutions for the users in vehicle. Because again, when we want to go for the on road, for the autonomous or the connected vehicle segment, let's say when you are dealing with the infrastructure, it is going to be those directions also, which where the SLM and cloud native LLMs will be playing a major role.
Thank you so much, Alok. It was really interesting, your presentation and the domain you spoke about. Thanks again for your availability and to contribute to the forum. I think it's time to switch to
Thank you, Danilo.
Young.
Thank you, everyone. Yeah.
Thanks again, Alok. Great talk. Hi, Young. It's your time. Thanks to join us. And title of your presentation is Memory Optimization for On-Device LLM, which is a great topic. So the floor is yours.
Okay. Hello, I'm Sonyoung from Kyung Hee University. So I'm very happy to share my recent investigation on memory optimization for on-device LLM. So before starting my presentation, I would like to briefly introduce myself. So I'm an assistant professor at Kyung Hee University, which is located in South Korea. So before joining Kyung Hee University, I was a postdoctoral researcher at ETH and research scholar at Virginia Tech. So my research interests include tiny machine learning, especially for memory optimization, and also compiler optimization for machine learning and real-time embedded systems. So our goal is to enable large language models on small computing systems. And we all know large language models are large in size. So the most popular models considered for on-device AI is LLMs with 7 billion parameters, which requires around 7 gigabytes for their model parameters when they are quantized for 8-bit precision. Since small computing systems have limited memory size around 4 to 8 gigabytes, the even 7 billion models hardly fit in their memory. So enabling on-device LLM is like putting a llama inside a refrigerator. However, LLMs actually need much more memory than that. So in the next slide, I will explain exactly for what they need more memory. So at first, I would like to start with the original transformer. So this is the overall structure of transformer first proposed in the NeurIPS 2017 paper. So it basically consists of a pair of an encoder and a decoder, where the encoder extracts the features from the input and the decoder uses the features from both input and output to make a prediction. Unlike the original transformer, many popular generative LLMs such as GPT and Llama are decoder-only transformers, which directly takes the input and makes a prediction based on the input. So in this talk, we will consider decoder-only transformers. So those decoder-only LLMs are often called autoregressive transformer, in that they generate a new token and append the new token to the input to generate the next token after the token. So for example, let's assume that the model is given an initial input, what is TinyML question mark. Then the model processes the input and generates the next token. So here the token Tiny is chosen as the next token. So then the token is appended to the input, and the model processes the input with the new token. So after then, they generate the token again after the new token. So the model repeats this process until it generates the maximum number of tokens or encounters the end of text token. So this recursive behavior is referred as autoregressive. So this autoregressive behavior requires one forward step per token generation. That means when the model generates n tokens, the model has to be processed n times in total. So therefore, autoregressive transformers may incur high computational overhead, and it makes it difficult to deploy large language models in small computing systems. Then how to reduce the high computation overhead of large language models? So nowadays, most of LLM frameworks support caching the intermediate outputs of attentions. So looking into the decoder architecture, it consists of a series of multi-head attention. So as the input gradually grows over time, they try to avoid duplicate computations between different forward steps. So the basic computation of attention is illustrated in this slide. So first, the attention generates the query, key, and value arrays by applying the separate linear layers to the input. And then it multiplies the query and key arrays and softmax the key QK array to compute to the attention score. So here softmax is omitted for simplicity, but it is applied to the QK array. And the output array is multiplied to the V array. So here, the key value cache is introduced to reduce the overhead of obtaining the key and value arrays. So as explained earlier, the new token is appended to the input every forward step. So therefore, we don't have to calculate the K and V values for the previous tokens. So then, instead of generating the key and value arrays every time, it stores the K and V values in the memory and reuses them for the next forward step. So since the linear layer, which entails matrix multiplication, is generally computationally very expensive, So using KV cache can largely reduce the computational overhead. So the memory usage of KV cache can be calculated with this formula. So the KV cache size is 2 times P times the number of layers and the number of attention heads times and the token dimension and W. So here 2 is multiplied because it has to store K and V, and then P indicates the number of bits for representing the K and V values, and then also here W denotes the context window size, which is the number of tokens to be used for generating the next token. So it is also called sequence length. So to show how large KV cache is, we measured the memory usage of a couple of large language models on top of the Llama C++ framework. So the graph shows the memory usage of each model for storing their weight, the blue bars, and KV cache, the orange bars, and the activations, yellow bars. So here it is shown that for 7 billion models, KV cache can be almost as large as the model parameter size. So in the case of Mistral 7 billion model, the size of KV cache is 4 gigabytes. So that is, if we quantize the model for lower precision, then the memory overhead of KV cache would become like dominant compared with the other components. So there have been various approaches to reducing the memory overhead of KV cache. So one popular approach is to redesign a model with a different type of attention. So as illustrated in the figure, multi-head attention is a typical type of attention used in transformers. And group query attention and multi-query attention are newly introduced types of attention, which can reduce the size of KV cache by using a less number of key and value tokens. So this grouped query attention is already applied to the Llama 2 model, which is one of the new features of the model. So another approach is to manage KV cache in a page fashion. So in general, KV cache is implemented as a ring buffer, but it may suffer from internal or external fragmentation when there are multiple users that shares a KV cache. So it can result in underutilization of the memory space. So therefore, this SOSP paper proposes to bring the concept of paging to manage KV cache. So it swaps in the cached values into GPU memory when they are needed. So, however, this approach assumes a very large system with multiple users and multiple batches, and also a dedicated GPU that has its own memory. So this approach is not appropriate for optimizing on-device LLMs. So to further reduce the memory usage of KV cache, we tried dynamically compressing KV values before we put the values into the cache so that they consume less memory space. So we investigated a variety of compression methods, so dynamic quantization, dynamic pruning, and dynamic dimensionality reduction. So first, I would like to discuss the dynamic quantization of KV values. So there are 3 main types of quantization. The first one is linear quantization, which is the most common type of quantization. And it chooses the linearly spaced values for quantization as illustrated in this graph. And the second one is log quantization, where the gap between 2 values grows in a log scale. And the last one is weighted quantization, which is relatively newer quantization method than the others. So the method clusters the values to reflect the distribution of values and then use the clustering information for quantization. So the histogram on the left side illustrates the distribution of KV values for some sample inputs. So first, we can see that the KV has a very wide range of values from -20 to 20. So while convolutional neural networks models usually have a much smaller value range of from 0 to 1 or -1 to 1, the deviation of values in KV is relatively large. So and also there are not many small values in KV, so we can only see a very thin bar in the histogram around the 0. So we measured the average contagion error to compare different contagion methods. So the results show that the contagion error decreases when the data precision becomes higher. So for the 5-bit quantization, it obtains the high compression quantization error, and then with the 8-bit quantization, it obtains much less quantization error. So when the precision is low, weight quantization obtained much less quantization error than the other method. However, with higher data precision, weight quantization does not perform very well. We guess that with high data precision, it has to have more clusters for quantization. So maybe it has some difficulty in finding a good clustering from the data. And we also tried unstructured pruning and structured pruning to compress KV values. In structured pruning, the values that are smaller than the pruning threshold are pruned separately. So in structured pruning, the entire tokens with small values are pruned from the token array. And compared to unstructured pruning, structured pruning has an advantage in storing sparse data because it does not need a very complex data structure to memorize the location of each value. So for measuring the compression error, we set the target sparsity, which gives a similar compression rate to quantization. So as expected, structured pruning obtained much higher compression error than unstructured pruning. But overall, unstructured pruning failed to outperform the quantization method. So as we saw in the previous slide, the KV arrays have like very few small values around 0. So pruning may not work very effectively for compressing their values. So lastly, we tried reducing the dimension of KV tokens using an autoencoder. So an autoencoder model consists of an encoder and a decoder, and where the encoder encodes the input data, lowering its dimension, and the decoder decodes the encoded data to recover the original dimension. Then we can reduce the memory usage of KV cache by storing the encoded data in the middle into the KV cache. So applying the dimensionally reduction dynamically means that we have to run the encoder and decoder in the middle of the model execution. Therefore, we have to make sure that the autoencoder should be lightweight enough not to incur large computation and memory overheads. Then we designed a very small autoencoder which applies one deconvolutions to each token of KV. Then it can like halve the dimension of the token. So we can formally define the compression overhead of the autoencoder as follows. So assuming that the encoder consists of two one-dimensional convolution layers, the number of floating point operation is approximately the token dimensions times kernel size times the input and output, the number of input and output channels. Then this compression overhead has to be lower than the GenV overhead, because if the compression overhead is higher than the GenV overhead, then there is no point of compressing KV values. So considering the compression overhead, we designed a very small autoencoder with 3 one-dimensional convolution layers and measured the compression error for comparison. So compared to quantization and pruning, the autoencoder suffers from high compression error, although some more optimization may be possible with by tuning the hyperparameters of the autoencoder. So here is the comparison table of the dynamic compression method. So in terms of compression error, we saw that the weighted quantization can obtain much lower compression error than the other method. So conversely, dynamic pruning obtained relatively higher compression error because, as we saw in the histogram, the original sparsity of KV arrays is not that high. And then regarding the computational overhead, the dynamic quantization incurs very low overhead because it only has to find the nearest value inside among the possible values. And then dynamic pruning requires some computational overheads for processing the sparse data, because it has to format the sparse data in with some sparse data format, such as compressed sparse low. So it incurs some overhead for processing the sparse data format. And dynamic dimensionality reduction incurs more overhead because it has encode and decode the data in the middle of the execution. And next, the memory overhead for dynamic quantization is almost none, because we only need to store a few quantization parameters for dynamic quantization. So, and then in terms of compression rate control, dynamic pruning can allow fine-grained control of sparsity by changing the pruning threshold. And then the dynamic pruning also does not need fine-tuning because it only prunes values that are less than the threshold. However, the dynamic quantization, especially weighted quantization, need fine-tuning to find the optimal clustering for KV values. So in conclusion, KV cache is introduced to reduce the computational overhead of autoregressive transformers. However, the KV cache can be as large as model size, which is not ideal for small computing systems with limited memory size. So this talk explores various methods for reducing the memory overhead of KV cache for on-device LLMs. So this talk shows that the weighted quantization can obtain high compression rate with small errors compared with different dynamic compression methods. So this is the end of my talk. Thank you for your attention, and I will be happy to take any questions.
Thank you so much for your great talk, Seon-Young. Optimizing the memory for LLMs and GenAI is a super important topic, especially with respect to the energy efficiency. Even if I'm not a great expert, maybe I would like to let you comment a bit about 2 aspects. One is about the KV cache, and in particular the axes. During your studies, did you observe the correlations that can be exploited in both the axes and the usage of the cache?
What do you mean by the correlation? The correlation between
correlation between axes over the time, or even the values which are accessed?
So between the over time, you mean correlation over time?
Yeah. Of the addresses generated, for example, you tend to access during the operation of the LLM this part of the cache, which is very close to another part of the cache, because of the natural, let's say, operations of the LLM. If there are patterns which are privileged.
Yeah, KV cache is not hardware cache, so it's stored in memory. So actually, it is accessed sequentially when the model generates its token. So I think the access pattern of KV cache is quite regular. So
the access can be even predicted ahead of time.
Yes. So yeah, it can like accelerate the access of the memory if we can like free fetch the KV cache for like future processing.
There is a question from Chris. Do you have example of compression on a common LLM?
Compression on a common LLM.
Yeah, maybe models from Hugging Face on which you tested more or less extensively the effect of compression.
I tested
and the techniques you mentioned during the presentation.
Yeah, I tested the dynamic compression methods with Llama 2 7 billion models. So yeah, you can download the Open Llama 2 models for Llama C++ framework. So I am considering opening my code for public, so that you can easily apply the dynamic compression for your any like large language models. So
that would be very interesting, yes, for the community, I guess. So yeah, when do you plan to do that in near future?
In near future, maybe before the 2024 ends.
Okay, thank you. In terms of implementation, did you also studied KV cache with respect to in-memory computing? So are there operations which could be nicely accelerated within the memory?
Okay.
Dynamic quantization, dynamic pruning, this type of operations that could have a place in some hardware tightly coupled or inserted within the memory itself, even if it is large.
That's a good point, because KV cache is for reducing the overhead of computing the K and V values. So I think if the dimension is very large, then it can be processed in memory, processed with in-memory computing without like a heavy like memory accesses from between CPU and memory. So I think there are many opportunities for processing very large data inside memory. But yeah, as far as I know, there are many approaches to apply like accelerate matrix and vector multiplication inside the processing in memory. So yeah. And also, I think the dynamic compression can be done inside the memory if we need to save more, reduce more computational overhead.
Do you think I'm trying to to look ahead? Do you think there are opportunities maybe for other type of LLMs, to push the dynamic quantization at the extreme, which means 1 bit.
One
bit
bit
per sample, per data.
Because I tested 5-bit quantization, but already it's suffer from like large quantization error, even with a 5-bit. Because I think for the weights we can apply like lower precision quantization, but for activation it is more difficult to apply the quantization because of the distribution of the data, because it depends on the input data. So it is more difficult to predict the characteristics of data. So but yeah, I want to more like investigate the data distribution to optimize the quantization method, because I think maybe the weighted quantization is not still suboptimal for large language models. So yeah, I think there is the next step to forward the research.
Thank you. And another question from Chen Liu. I just ask Arniban one further minute of patience, please. Chen Liu is asking, how do people manage memory of KV cache in hardware like GPU? For example, reserve a maximum token size and update KV cache token by token, or allocate new memory section for each new token of the cache? That's the last question for you.
Yeah, that's a good question. So I tested the measure the memory usage on top of Llama C++ framework. In the case of the framework, it allocates the maximum token size, the cache KV cache for the maximum token size. So it reserves like large space at the beginning, and it gradually like put tokens inside the KV cache. And then yeah, so I think the paper I introduced in the presentation wants to move from the fixed allocation to paged allocation to reduce the internal memory fragmentation.
Thank you so much, Chen. It was really appreciated your time and your contribution for today. Thanks a lot also for your availability to answer some question. Really appreciated the Sen Yong.
Okay, thank you.
Time to switch to Arnibal by Sen Yong. Thanks, Arnibal, and apologize to let you wait a little bit. Then now it's your time. Your talk is GenAI-based custom code assistant for AI PC, and the floor is yours.
Thank you, Danilo. First of all, I would like to thank the TinyML Foundation for this wonderful session, and happy to be part of this. Yeah, next slide. So just a brief introduction. So basically, I am working as a solution architect in the embedded software practice, part of Wipro engineering. And basically, I come from an embedded and digital signal processing background, and now very passionate about working in AI ML related to embedded systems. And to introduce to anybody who is not aware, so Wipro is a leading global information technology and services company. And we from Wipro Engineering are part of the group which work on engineering services and research and development. For this work on the custom code assistant on AI PC, I would like to acknowledge few of my team members like Rupesh, Deepak and Sagar, who are part of the Wipro engineering team, and also the Intel team who enabled us with their AI PC platform. Yeah, we can go to the next slide. Yeah. So basically the problem, what we are seeing is that today with Gen AI, there is a lot of opportunity and also hype. And there may be still certain doubts that how effective it is going to be. But in one area, it is very clear that the things are changing very fast, and that is the way that software development is going to happen. So already we see an adoption of lot of commercial general purpose code assistants, namely GitHub Copilot, Codium, and many other tools, which are increasingly being adopted. However, the approach that we are taking is that though these general purpose code assistants would be good for some specific coding, but we see a need that many of the enterprises are sitting on a large code base of very proprietary code data. So they may not be very open to share it directly with many of these code assistants, which basically leverage cloud-based and at best a hybrid approach. So what we are proposing here is a device-based solution, like a complete edge-based solution, which is deployed on an AI PC, and it utilizes the basically facilities provided by the hardware, and runs in a very optimized way on that. Maybe next slide. Yeah. So in terms of the enterprise software developers, few of the challenges which are seen are that the technology changes are very rapid. So people have to quickly learn a new programming language, and they are having very stringent productivity goals. Like what took 6 months previously now needs to be done in 3 months. So how can this be done? So this can only be done using certain intelligent tools in terms of helping you in the coding, helping you in debugging or optimizing the code which you have written manually, and also in basically understanding the legacy code base, which doesn't have the required documentation or design documents available. Also, in meeting these challenges, there are certain expectations for any of these assistant tools. So these tools have to be provide the results in very quick time with low latency. People still don't want to pay the recurring cloud billing costs for, say, thousands of their employees in a large enterprise. And the accuracy of these assistants are very important, because if the results are not accurate enough, then these won't be successful. Hence, we see the need of a custom code assistant which can be tailored for every unique solution situation for our customers. Maybe we can go to the next slide. Yeah. So this is the solution that we are building. It is a complete web-based application, and it can take in the inputs in terms of the source code files or the folders, and also the developer can paste the code. In future, we are going to extend it to read like, say, GitHub repositories and so on. And then we give an option to do whatever operation you want to do. Like, for example, you have the code base and you want to add comments to that code base, you can do that. You want to create a summary of your code. You want to chat with your code and ask specific questions about specific functions. So all those kind of features are supported. How do we check how good this solution is? So some of the key metrics that we are measuring here is basically how correct the output is or how useful it is for the developer. Then what is the response time or the throughput in? So all the responses should be in the order of milliseconds. Otherwise, it defeats the purpose. How good does the tool understand the context and how user-friendly it is? And some of the key parameters, like in addition to performance, is like what is the performance per watt? Because increasingly the energy efficiency is also becoming very important. We can go to the next slide. Yeah. So here we have shown a high-level architectural diagram of our solution. So mainly we have an UI or an input module, which also does the pre-processing. And the data set we have used is a completely proprietary code base, which was our own code base. Then we have the orchestration layer where we use certain frameworks like LangChain or Llama Index. And we use a mixed methodology. So we use retrieval augmented generation, as well as we take some of the open source models like CodeLlama, StarCoder, and CodeGemma. So we have taken these models and we tried fine-tuning them, and then we did a benchmarking and then selected the one which gave us the most accurate results. Ultimately, we again used, because we are using the Intel platform, so they have a framework for optimized inference on their platform, which is called OpenVINO. So we converted the model into the OpenVINO format and optimized it on their platform. The other important part is the human feedback loop. So based on the human feedback, we try to fine tune the model and improve the accuracy of the solution. Maybe you can go to the next slide. Yeah. So this gives a view of the Intel AI PC platform and what are the processing elements which are part of it. So it consists of the Core Ultra series of processors. The CPU itself has a deep learning boost accelerator, which accelerates the AI tasks. Then we also use the integrated graphics, which is the Intel Arc graphics as well. They have a discrete graphics. Also, mainly they have this Intel's neural processing unit. So these neural compute engines do the compute acceleration for all the AI tasks. And in order to compare, so the CPU is very good for low latency and fast response. The NPU is good for overall efficiency, like it gives a decent throughput with good energy efficiency, and GPU is good for overall throughput. So depending on the use case, we have orchestrated our workload on the right processor. You can go to the next slide. Yeah, so here we give a summary of some of the key features that we are adding. So one key use case we see is that a lot of the legacy code doesn't have proper design or documentation. So if you want to automatically add the comment, so it can be very easily done through this kind of tool. For a new developer who is coming on board to the team and is not having much idea, so the code summarization can generate an accurate summary of the code. We can give instant code suggestions and auto completions based on the current context when the developer is doing the coding. And also the tool can help in terms of error detection, debugging, identifying potential errors, and so on. If we have a legacy code and we want to optimize the code, then the tool can give the proper suggestions regarding it. Some of the use cases we see from our customers are like reverse engineering the artifacts. So like the code is present, but no requirement document is available. So whether we can generate the requirement specifications from the legacy code. Another unique use case is like code conversion. So we have, say, C code and we want to migrate it to C++, or we have a version of code in C++ 17. So we have to migrate it to C++ 23. So doing it manually is quite cumbersome. So these kind of tools can really hasten the process. Can go to the next slide. Yeah. So what are the solution benefits of this edge solution? Primarily, it helps us in saving the recurring cloud costs, because this is completely on the device and there is no need to connect to the cloud. It is a very secure solution because it runs on the local environment and ensures that there is no leakage of information, because the enterprise data is highly proprietary and confidential. This kind of solution can be a low latency solution when once it is optimized to run on the underlying hardware platform, and it is very efficient provided that the workloads are properly orchestrated between the CPU, GPU, and the NPU. Due to the availability of the NPU, the overall power consumption can be greatly reduced. And the Intel OpenVINO framework helped us in optimizing the model, which is ultimately deployed on the underlying platform. Coming to some of the business benefits, the developer productivity can be greatly improved because the time needed to understand the existing code base gets readily reduced. So in especially systems programming, we have a lot of firmware code which are very uniquely written, and for example, the BIOS code. So for a new developer, it's always very challenging, and these kind of tools can greatly help them. It improves the code quality, ensuring that the code is syntactically correct and optimized, leading to lot fewer bugs and much better performance. These kind of tools can be readily integrated to the developer environments like VS Code and others. Um, it can continuously learn from user interaction to provide increasingly accurate and relevant suggestions, which are also personalized. A lot of the enterprise companies have their own coding standards, and if you want to ensure adherence to those standards, then these tools can easily integrate those standard documents and ensure that we can talk about the code to requirements, which was discussed. And also, as I talked earlier, so the faster ramp up happens for new engineers. We can go to the next slide. Yeah. However, while implementing this solution, we saw that there are certain challenges. So many of the things which should work in theory, but when we actually implemented it, we saw that the accuracy is highly important, and one technique doesn't work for every use case. Um, because if the output itself is not accurate enough, then this tool can't be used. Then user acceptance has to happen, because developers may be apprehensive about using these tools, and so only when they are trained and once they get used to it, then they understand the possibilities and the limitations of this tool, and then they can use it effectively. Being a completely edge solution, and since we are running Gen AI models, so there are certain minimum resource requirements. So the disk space or the memory at least has to be in the order of gigabytes, and only then this kind of solution is feasible. Yeah. So what we see is that the custom code assistant can really become a significant help in the field of software development. by leveraging AI technologies, it will enhance the coding quality and provide real-time support to the developers. So whatever challenges are there, but the benefits far outweigh the challenges, making it a very promising solution. Next slide. Yeah. So here we have some pointers on the future work that we are planning. We are planning to support more programming languages. Currently, we are targeting systems programming languages like C and C++. We want to improve the natural language processing engine so that it is able to understand the context and the background of the queries coming from the developers. We plan to integrate this more with more in IDEs and version control systems. And another topic would be how we can adapt to the developer's coding style and preferences for the future. Yeah. So that was all I had to share. Any questions I'm willing to take.
Thank you so much, Anirban. Yeah, you touched a really important topic about the code assistant. And I think many of us on daily basis are sharing and using the code, are sharing the needs of the code assistant and using them for increasing the productivity. Now, a question about that is, can you share your experiences about measuring the productivity? What would be a meaningful procedure to objectively measure the impact of such a code assistant in everyday life of the embedded programmer, the C++ programmers?
Yeah, I think that is a very important question, what you put. So I think we are still exploring how best to measure the productivity. But to take an example, what I would say is that um, typically so for example, we did some training on certain code assistants, and um, basically what we thought is like we took some task, particular specific task, which maybe in a manual method say takes like 2 weeks, right? And then we challenged ourselves and saw that whether with the code assistant we can do it in a reduced time frame, for example, that specific task. And if it is achieved, say the task of say 2 weeks can be done in within 3 to 4 days, then it's a real gain in the productivity. So now how do we scale that for multiple engineers and all? So that would take a more detailed approach. But typically, like with certain training workshops on these coding assistants, you can at least get a feel that a particular task which could take 2 weeks now can be done in say 3 days or 4 days. So that is the productivity gain you get, and that is by having multiple developers using these code tools in as part of a say training or a workshop of a short duration. I think that is one way we are basically evaluating.
Thank you, Arnival. One question from Sandeep. How much RAM is needed on the AI PC for the use cases presented?
Yeah, so typically these kind of AI PCs like have at least 16 GB to 32 GB RAM, like depending on the configuration. So that is the configuration with which we have checked. And what we saw also is that the GPU, the performance is much better, definitely when we have a discrete GPU, and the NPU is also performing quite well. With the CPU only, the performance really is quite poor, because it goes to the order of even minutes for any simple response.
Thank you so much. Another question from my side. I really like the topic because I'm a fan of the tools that really introduce automation and increase productivity. Is also part of my job. So I'm wondering, in your experience, what could you say about the acceptance rate, in the sense that, for example, do you see more young professionals eager to be assisted by such facility, less the seasoned, experienced programmer, or what other mix you are experiencing?
Yeah, I think the young developers are more interested and more ready to adopt these kind of tools, because they want the shortest way, right? Whereas, for us who are more coming from with the baggage of having done manual coding and programming, I think maybe there may be an initial reluctance till we can see the benefit of it. Um, and I don't think there is a silver bullet that these kind of assistant tools can solve all your problems, but it can really improve your productivity, definitely.
And in such a case, for the people that is, for any reason, more reluctant, or delaying, procrastinating such an adoption, in your opinion, what a company employing such people should do to move really move forward the adoption? So any procedure, any training, any special initiative you would envision to increase the steepness of the adoption rate?
Yeah, I think say boot camp or like a very short, intensive training session, say 1 day, 2 day sessions, they really help. Because first of all, when a trainer comes and shows you the benefit or helps you, and in my experience, it need not be like if you are a C++ programmer, you may also do a workshop in say Java, okay? At least you see the benefit of the productivity gain that you are getting out of the tool, right? Once you are convinced, then being the expert programmer that you are, I think you will find your own ways to get productivity in your work and find the right set of tools as well. So what we have seen is that intensive training sessions of say 1 or 2 day duration, they really work. Like they first of all remove the inhibitions of the people, and they see that okay, this is at least working in say the Java world, and it should also be working in systems programming, for example. So that is something what I have seen has worked.
Yeah, very good. And last question before to move to the next speaker. I think we have still a couple of minutes, Anirban. Generating C code, C++ code, make it fast running on the target can be also helped by profile-driven optimization. So I run the code, I get some profiling, and then maybe the code could be improved. Some kernels could be improved to make it faster or less memory demanding. These type of things. Is that part of is or could be a part of the code assistant, or maybe is not required by the inner processes of generating the code?
Yeah, I think, in my opinion, it is something which you can add as an additional feature, but this is not the real problem that the generative AI can solve. What we see from a generative AI perspective is like, you have a firmware code, okay, like which has been written, say, 15 years back. A new developer comes to the team, has no idea on that code, doesn't have any documentation because it doesn't exist, right? In that case, this kind of tool can actually give you a good summary, okay, help you in understanding the code much better. And these are the real use cases that can be solved. The optimization part, I would say, is more like an add-on because there are already sophisticated tools which can do that.
Thank you so much, Anirban. Thank you so much for your time, your contribution, which was really much appreciated by me and by the TPC committee. Thanks again. If you have time and there are questions in the comment chat, please consider to target some of them.
Sure.
Otherwise, thanks so much again for
Thank
your
you,
time.
Danilo.
Really.
Yeah, thank you.
Bye. And welcome to Alberto. Last but not least, Alberto will talk about neural style transfer for microcontrollers. I see also the logo of ST, so please explain your work and let's see what you have to propose. Thank you.
Okay, so thank you, Danilo, for the introduction. So, as you said, this work is titled Neural Style Transfer for Microcontrollers, and it's done in a collaboration between FBK and ST. And so we are going to change a little bit the topic because I'm sure you've all heard a lot about generative AI applied to text in this forum. And actually, in this presentation, I'm going to change a little bit the topic, and we are going to go to image generation, actually, with generative AI. But this is always targeted at very small devices, and in particular, this work targets very, very lightweight, low-power devices, such as microcontrollers, and that's why ST is fundamental. So, if some of you are not familiar with the task, what we are doing is called neural style transfer, which is an image generation task. And it has particular applications, fun applications in like synthetic media generation or generating artistic renditions. But it has two very practical uses, which are in anonymization and in domain adaptation. The problem of these networks that usually do neural style transfer is that they are very, very large and very, very slow, and they are definitely not fit for tiny, low-power embedded devices. So if any of you are not familiar with the task, I'm going to give you an example of what we are trying to do with the help of my cat. Okay, this is my cat. Her name is Enea. And no, the picture is not upside down. She just sleeps like this. But so what neural style transfer is, it's a task of merging the content of one image and the style of another one. So for example, here in the center, we have the content of our image, which is like my cat. And if I go, here we can see my cat, but painted by Van Gogh. Okay, you see the content image in the middle, you see the style image on the left, and you see the generated image on the right. So we are copying the content of one and the style of the other. So these approaches are not new, actually. They were born around 7-8 years ago. But the problem is the first paper that proposed networks for this task used an iterative approach. So you needed to run the network like hundreds of times for a single image, which was definitely not very, very fit for embedded devices. And then, okay, we moved to feed-forward approaches, and we moved to CNNs, but still very, very large convolutional neural networks, okay? We are talking tens of megabytes, or 400 megabytes, 80 megabytes, nothing that can actually fit a microcontroller. So I will explain a little bit how these approaches work. And actually, the inference of these approaches, it is very simple. We just have our content image, we have our style image, and we have our style transfer network. And obviously, we just feed content and style inside of our style transfer network. And what we get out is our styled image. This is very simple. The fun part of how these approaches work is actually the training. So to train these approaches, you actually need a separate neural network, okay, a separate feature extractor. In this case, we are using VGG19. And how we are using it and how it is generally used in these approaches is we are obtaining a style loss and a content loss from the features in these neural networks. And in particular, we just say that, okay, the features in the first layers of our network, they represent in some way the style of our image, because the first layers of VGG19, they are trained to understand color, lines, shapes. Okay, so high frequency stuff more related to the style of an image. And while the later layers of an image of VGG19, they are trained to understand the higher level content of an image. So they are understanding like there's a cat, it is upside down, the eyes are yellow, and stuff like that. So in some way, if we can reproduce the first layers of our style and the last layers of our content, then we are generating an image that is perfectly doing style transfer. So we want to do this very small, and we are not really interested in the training part, so we can actually ignore VGG19 for now. What we are focusing on is the first part, which is the style transfer network. If we want to do this on embedded devices, if we want to do this on microcontrollers, we need a style transfer network that is much smaller, much faster, and much more fit for microcontrollers. And for this, we actually chose this network here. So this is a AXINET. It is a network that was developed here in FBK, and it is a CNN that is specifically designed for generative tasks, so generative AI on very low power embedded devices. Okay, and this is done because, okay, our network, the convolutional block, is designed using the operations that we have benchmarked to be maximally efficient on a very large set of devices. So we just took like some commonly used CNN operators, such as COMQT, depthwise, pointwise, grouped convolution, stuff like that. And we just got all the embedded platforms that we could find, and we benchmark each operator based on efficiency. And we defined efficiency as the performance that we achieved on that operator, divided by the energy usage of that particular operator, because some are slower, some are less optimized. COMQT is generally very optimized across the board. So with the most efficient operators that we found, we designed our convolutional block, and we actually have downsampling and upsampling blocks, so we can use the network for generative tasks. And another cool thing about this architecture is that it allows what we are calling hardware-aware scaling. So what is hardware-aware scaling? Well, embedded devices, you have a great variety of platforms that you can use. You can go from a very tiny microcontroller to a parallel platform, to a TPU, to an accelerator, stuff like that. So how can you design a network that can fit your particular device? So what we are doing is we are describing each platform with just 3 numbers, which are the amount of flash, so storage space that you have, the amount of RAM, so working memory, and the speed of your CPU, so how many operations you can do in a second. And based on these 3 numbers, you can just change 3 hyperparameters of the network, which are the ones here in the slide, alpha, beta, and gamma. And with each one, you can optimize a separate parameter. Okay, let's say that our original network takes too many operations. We just go down in alpha, and we get a network that uses fewer operations. And you get a very good network for your platform, and you get a network that can maximally utilize the hardware provided by your platform. So here I have an example of what happens when we do this with our style transfer network. And in particular, here we have a small breakdown of the original style transfer network that we were using. And you can see that we are using a big amount of RAM, 21 megabytes. We have a lot of parameters. We require a lot of operations. These are generally not very big numbers, but if you're considering a microcontroller, they are very big numbers. And in particular, yeah, I forgot to say, our target platform it is the STM32H7, which is a microcontroller with 2 megabytes of flash and 1 megabyte of RAM, and it can run around 60 million operations per second. So the numbers here in the slide, they are way too large for our use case. So what we do is we design our XINet using hardware scaling, and we make it actually a little bit smaller than what we can achieve with our platform. And you can see here that we can manage savings of like 96% in RAM, 90% in number of parameters, and 97% in the number of operations. So the network is much smaller, it is much, much faster than our original one. However, we do have a small price to pay. Obviously, we are approximating a network with something that is 1/100 of the size of it, so we are losing a little bit of performance. Let me introduce briefly the metrics that we are using. So for style transfer, we use these two metrics mainly. FID is how close you are to your style reference, and clip score is how close you are to your content reference. And ideally, you want to maximize them both. So as you can see here, we lose like 15–20% in both these metrics just by using our approach. So the question is, how can we get back this performance that we lost? So one way of doing it would be trying to make the task a bit easier for our network to learn. Our network is very small. If you can make the task a bit easier to understand, then it will perform better. And to do this, we are going to slightly change the loss function, so the one that I showed you before with content and style loss, and we are going to add a couple of modifications to it. The first one is we are logarithmically scaling the features inside of VGG. This sounds very complex, but actually what we are doing is just what you can see here in the slide. By doing this logarithmic scaling, we are making like small features more expressive. Okay, you can see them a lot better. The feature map is more expressive and more easy for the network to approximate. And the other thing that we are doing is we are running the style transfer operation in a multi-scale manner. So this helps a lot because if you imagine, for example, the Starry Night, well, in the Starry Night, you have the very, very small brush strokes, but you also have the very large swirls around the image, and you want to approximate them both. So by doing this in 3 different scales, we can actually learn the task a lot better than just using a single scale and a large network. So by doing this, you can see that we get a lot of the lost performance back, and we are actually around 5 to 3% worse than the original approach by saving like 97% of the network, which is quite a good result already. And I can show you some results obtained by this approach. And so here is my cat again. And this time it is styled with like a stained glass look. And you can see that the image is quite nice. It is quite consistent. The colors are there, the lines are there. And here instead is a view of Brixen, which is a city here near Trento. It is already quite pretty, but after we run a style transfer, we can make it a bit more detailed, a bit more colorful, a bit more artistic. However, we still do have some problems. If we try to run, particularly related to color, if we try to run this approach as is, using the Starry Night as our style, what we get is this. And you can see, and now the image, yes, it is styled, but it is very, very blue, okay? And this makes sense because our style reference is blue. So what is happening? Well, as I said before, the first layers of VGG, they are learning stuff about the color. So if you provide VGG with a style reference that is blue, well, then your network will learn that the generated image must be blue. But we don't want this because, especially if you want to use this for anonymization, well, you cannot just have a uniform color across your frame. So how can we solve this? We solve this adding an additional loss term, which forces the generated image to take the color from the content instead of from the style. And to do this, we just converted both generated image and content image to the LAB color space, where you have one channel for brightness, which we are completely ignoring. And then you have 2 channels for chrominance. And we just try to match as closely as possible the chrominance of the generated image and the original content image. And so here you can see the effect that this has on our cat. And you can see that the rendition of the image becomes much, much better. Okay, we can actually carry the colors from our content reference a lot better to our generated image. And obviously, this is an additional loss term, so you can adjust a little bit the weight of this loss term. You can have a generated image that is closer with, in color to your style reference, or an image that is closer in color to your content reference, okay, depending on the application. So then we try to run these on another picture of my cat, and we find another problem, okay. As you can see here, we have another picture of my cat, and then in the generated image, we are actually losing the cat, which is quite a big problem. Not really for artistic renditions, but it is a very big problem if you want to do this for anonymization, because if you are removing your targets from the frame, then it doesn't really make much sense to do this as anonymization. So, well, why is this happening? The problem now is actually the content loss. Okay, the content loss, I was telling you before, it is calculated at the final layers of VGG19. But the problem is the final layers, they have a smaller and smaller spatial resolution. So they can actually miss some small targets. And so how can we fix this? Well, to fix this, we are going to resort to the clip vision transformer, which is the clip foundation model. It is not directly related to the metric that I was telling you about before, so don't mix them up, keep them as separate things. Okay, the clip vision transformer is the pair of these two models, one working on images, one working on text, and they are trained to project image and text in a shared latent subspace. Okay, very complicated way of saying that they are just obtaining the same representation for the image and for the text. You can imagine, like, for example, here, these orange features that you see, they are containing the concept of orange, of bag, of cat, and they are the same features extracted from both the image and the text. And this actually helps us a lot because in some way you can think of clip as providing captioning for the image, so providing you a description of what's in the image. And so what we do is actually we run a clip on the generated and the original image during training, and we obtain the two semantic representations. And from this, we try to line them up in such a way that they represent the same stuff. So you can see here from the original image, we have a representation that says, like, okay, there is a desk, there is a bag, there is a cat. And from our generated image, it will be a bit different, but it will still say, oh, there's a desk, there's a bag, but there is no cat. Okay, so they are quite different. We have an additional loss term that forces these two representations to be the same. So in some way, we are distilling the concepts learned by clip during training. Okay, and we are forcing the two images to represent the same stuff. And here you can see an effect of this. Okay, on the left, we have our original image, and on the bottom, you can see some text, and you can see the score, the correspondence score between that image and the text. And obviously, in the first picture, it is quite perfect. While in the second image, we are missing the cat, and this correspondence score is quite poor. In the third image, our style transfer network learned to put back a cat into the picture, and so we obtain a better correspondence score. So here is a small breakdown of our complete training approach. Okay, you can see that for each image, you need to do 5 inference passes, 3 through VGG19 and 2 through the clip image encoder. And so, yeah, the training is a bit complicated, but because our network is so small, actually the training just takes a couple of hours on a recent GPU, so it's not really much of a burden. Okay, so here you can see some examples of this run on, like, the view from outside my office, actually, which is already quite pretty, but we can make it prettier with Van Gogh's Starry Night. And there is my cat again, and there's my cat painted by Van Gogh. And so at the end, we obtain a style transfer network that works quite well. Okay, we almost match the performance of our original network, and actually the clip score becomes even better than our original network because we are optimizing in some way this clip representation. Okay, so we have our style transfer network that works pretty well, and here's where ST comes in, because together with ST, we worked on the deployment of this network on 3 different embedded devices to test their performance, and in particular, we chose 3 different families of devices. We have our H7 microcontroller, which is the one that I was telling you about before, okay, the one with a couple of megabytes of RAM, of flash, and 1 megabyte of RAM. And then we have the STM32MP2, which is actually a microprocessor, so much faster, higher power consumption, much more memory, and it also embeds an hardware AI accelerator, so it can make convolutional workloads a lot more efficient. And then we have the STM32N6, which is actually an unreleased board by ST, and it is a microcontroller with a low-power AI accelerator. Okay. And also in this case, this helps a lot with this kind of workloads because it can compute convolution quite efficiently. So here we have some results, and if you want, you can get the code from the QR on the top right. Okay, so we will start with the N6. We achieve image generation of 1 frame at 60 milliseconds, which is very, very fast actually. And also on the MT2, 72 milliseconds, it is very, very fast because this approach is like state-of-the-art approaches. They can reach 1 frame per second on GPU. Okay, so having an approach that is this fast on a microcontroller, that is a very good result in my opinion. We also tested it on a Raspberry Pi 4. We can still reach around 10 frames per second. We tested it on the MP2, so the microprocessor, but without the AI accelerator. And we still managed around a couple of frames per second. But the most impressive result, in my opinion, is the last one, because on the H7, on a pure microcontroller, we are actually running the image generation pipeline. Okay, it is quite slow. It takes around 8 seconds per image. But as far as I know, this is the first work that can actually generate pure images on a single microcontroller without any external help. So, in conclusion, what we achieved was we proposed a lighter network for neural style transfer and actually generative tasks for low-power embedded devices that can run in real time on these devices. And we also propose a couple of ways to improve the existing neural style transfer approaches with these additional loss terms that I explained you. And also, before I was telling a bit about anonymization. So here I have a very, very preliminary, very, very small demo about how this works. I hope this it doesn't work on the... Wait, how can I start the video? I should... Okay, here we go. This is a video of me walking across the frame. And here you can see the anonymized versions with like 2 different styles. And what you can see is actually the video flickers a bit because we are doing it frame by frame, but the action is really consistent across the 3 different videos. And we are actually changing everything about a person. Okay, we are changing the hair, we are changing the clothes. So this is like much, much better than doing like pure anonymization, like by blurring the image where you cannot recognize the action that is being taken, or just blurring the face where you can still recognize the person by looking at how the clothes and stuff like that. So this is a very preliminary version of how we can anonymize the video based on this approach. So that's it. Thank you a lot for your attention. And if you have any question, I will be happy to try and answer them.
Thank you so much, Alberto. Really impressive amount of work and very, very nice presentation, almost image-based. So very, very cute. Let me check if there are comments. Yeah, amazing work from Damien. Maybe I could ask you, what about audio? You spoke about the techniques in order to, it was in the previous slide, but you had a different way to match semantically the information between the original image and the text and the style to be overimposed. So it's not a simple overimposition, what you achieved clearly. I wonder if the techniques can be applied in a more generalized way also to other content, for example, starting from the audio.
Yeah. Actually, this is a very good question because we have some ongoing work that is using XINET and the same architecture that I showed you here applied to spectrogram and applied to audio generation. So that demonstrated a bit that this approach is quite general. Yes, you need to change a little bit the loss function, because what I am explaining here is more related to the image domain. But actually, the general technique and the network itself can work very, very well for audio. And also in that case, we are achieving some very great savings compared to other audio anonymization techniques.
Okay. I was wondering, I've been challenged by a comment from a friend asking me what kind of impact this technology can have on the market in the community. So let me forward to you this. I know you are not a businessman, so clearly, but I wonder, at least in which direction this technology can really provide an impact. You spoke about anonymization, concealment. Maybe I don't want to share my nose or some part of my body, or I want to preserve a kind of personal information that I don't want to share, at least at the beginning. But then maybe.
No, that makes a lot of sense. Actually, the way all of this was designed was always having an eye on public-facing circumstances. Let's say you have a camera that is in a public space. Well, maybe people there don't. Maybe you want to, in some way, understand if there are some anomalies, or what actions are being carried out, or just more simply doing, I don't know, people counting, stuff like that. Well, maybe people there don't really want to have their privacy broken because you are sending away a video of their faces like that. So in that case, having something that can anonymize stuff and that can actually guarantee you that you are keeping all the objects in the frame, and that's why I was telling you about the clip loss. So the problem is, if you have very small targets, because the camera is very far away, then you tend to have the risk of losing targets. In this way, you are actually more or less guaranteeing that you are keeping all the targets between two different frames, and you can run your high-level image understanding pipelines without worrying about people's privacy and sending faces and dealing with all of that. Also, in the case of GDPR and privacy laws, you can actually be quite sure that everything is being anonymized, because you saw from the video there was no way you would have said that the person in the same slide was me. So yeah.
Yeah, thanks a lot, Alberto, because I think now I see a useful application for everyone without falling in the danger of creating fake content. Because if I can improve artistically my content and still not be fake content, I think there is a value. There is a value, because it helps my image, my way to communicate with the others. Now we have a couple of questions the first from Chen Liu. So complimenting, great job. So what's the complexity of the final model in your demo? Like how many million parameters and how many GOPS, giga operation per second, it requires per inference?
Okay, so the model at the end, the smallest one, which is the one that we have benchmarked here in the slides, and the one where I showed the FID and the metrics, it is the one designed for the microcontroller. So it is less than 1 million parameters, and it is half gigaops to run. Obviously, the complexity depends on the size of your input image. In this case, this 500,000 gigaops is related to a 160 by 160 image. Actually, we also have in the GitHub repo, we have a couple of more models targeted at a Raspberry Pi or the MPU, which are a bit bigger. And in that case, the input resolution is 320 by 320. So yeah, for 2 gigaops for the large ones, half a gigaop for the small one for the microcontroller.
Thank you. Thank you to answer to Chen's question. Brenda, you deployed to multiple STM boards. Is your model hardware aware, or you can achieve similar results with the target agnostic approach?
So, well, when I talk about hardware-aware scaling, I made the example of the network that we have developed, and that is the one that is targeted to the STM32 microcontrollers, so the H7. But we actually run that on a lot more devices. Yeah, you can make a small network and run it wherever, and it will run faster on a Raspberry Pi than on an H7. But you can also, if you want maximum performance, you can just design your network for your Raspberry Pi, and you can just force it to use how many million operations that you want. And in that case, you have a very high performance and the frame rate that you want to guarantee. So it's very, very flexible. But yeah, in the GitHub repo, you can find a couple of networks that are more or less platform agnostics. Okay, they can fit a microcontroller, but you can put them wherever you want.
Thank you. And another question from Chris. Do you have pointers to references on the hardware-aware scaling? Is that an available tool?
Yeah. So regarding the hardware-aware scaling, you can check out the paper about our network. You can find it looking for XINet, X-I-Net, and it has been published at last year's ICCV. And you can look on GitHub for Micromind, and it is the tool, the toolkits that we use to develop these networks. And there you have a lot of stuff already pre-programmed to experiment a bit with this hardware-aware scaling approach.
Thank you. We can stop here, but Alberto, please take some time to answer to Ponam in the chat. He's asking to share the link to the GitHub.
Yep.
Thanks a lot, Alberto, especially to be the last one and to stay still with us and to contribute even if it's late. I know you are in Trieste. Thanks a lot for your contribution, and really was different from the others. And thank you. Bye.
Thank you for having me.
And now we are back to the recap with Davis and Pete. I think it was a great day, Pete and Davis.
Man, my head is exploding right now.
Yeah, Danilo, your endurance is impressive, and I think the engagement from the comment side is impressive. It's hard. I think this is the hardest part of the day. It's like where to begin to recap. It's got to sink in. Need to sleep on it. Yeah.
Yeah, I think there were really diversified contributions, which express somehow the richness of the people we have in the community.
Yeah.
Agreed.
Yeah.
Agreed. Some things stay the same and some things change. Like there's always great to see the continued interest in pruning and quantization and some of these familiar topics, but they take different forms in terms of the methodologies they're applied to, but also the diversity of technical details plus some applications like we saw with Alok's automotive presentation was a good deep dive on a specific domain, I thought.
Yeah. Well, that made sense. I like also the memory optimization discussion. Kind of went to math camp for a little bit there, but for a lot of these systems, they're very kind of memory bound, and that's cost. That's cost and power. When you get into these edge platforms, so the ability to sort of get more creative with memory usage is really going to help a lot of the generative AI deployments out there on the edge. Not really an issue when you're in the cloud. You just kind of throw in sort of infinite memory there, but out in the real world, you need to sort of be careful about how much you add in. So, but that was interesting.
I was also touched by some comments from Dave at the beginning when he was sharing his view about this layer representation of the edge. Edge is not a monolithic thing. It really is composed by layers, and really this layer are the opportunity for us and for the community to contribute. And the other point was really the concept of the infrastructure. AI is an infrastructure. I think is really a very important comment from Dave. infrastructure like a train, like water pipe, like energy distribution, which is amazing, and it means that is here to stay for long, and is a continuum between the cloud and the edge.
Yeah, Dave's onto something. Yeah.
It was interesting to hear. I mean, the way they do the real research with, Fortune 500s and kind of trying to understand where their head's at. And it was interesting that he was pointing out too, I think, reinforcing the fact that there's always a gravitational pull toward the edge. Things start as a POC on the cloud, but then when they get real and get commercialized, everyone's like, do I need to pay all that cloud stuff? And do I need to can I just have this in a box on my factory floor and do that? So I think that's just always the gravity,
Once you get that first AWS bill and you think, but the one data point from Dave's slides, I think he was talking about the percent increase, the uptick in evaluation. So people at the evaluation stage of AI, the one data point that stuck out to me was the percent not interested in using Gen AI. It was very small. I think the global average was like 5%. I think Europe, EU was highest with 11%. I mean, so yeah, it's here to stay, and manufacturing intelligence.
Yeah. I was at Embedded World last week. I did the rounds. I mean, it's still early. So I asked people, some of the box makers, that make gateways. I'm like, what do you have for me to run like a Gen AI model, like in your actual gateway? Like, what do you have that's outfitted with that? And, it's still pretty slim pickings. It's some Orin based stuff with, 32 gigs of RAM and stuff, but that's like $5,000+. So I think that's the next thing, is like, now we'll start to see some of the box makers, the device builders, building out platforms that are edge AI capable. I mean, Qualcomm makes a pretty good case with their Snapdragons on what they can really do there. And I think we'll see more and more, and I'm sure with NXP and folks as well. But that's the next thing, is to see actual equipment out there. So when Dave talks about evaluating, how do people actually evaluate this stuff in a cost-effective way? I think that's the next step.
I think ST and Qualcomm, you guys just partnered up, announced some partnership along these lines of combining computation plus connectivity.
Yeah. So it's going to get real. I'm sure by the next Embedded World, I'm sure we'll see all kinds of stuff going on. But even 6 months from now, it's inevitable if there's demand. So yeah, I thought the range of stuff was really good. The Executorch stuff, I learned a lot on that from Meta, from Chen Lai. That was cool too. Mentioned the BOSCH stuff. Yeah, it was just like so many different ways. I mean, there's an old phrase, there's never a shortage of work to do. There's like a ton of work to do here, but a lot of opportunity for people out there that are building out their careers and want to really be on the cutting edge, no pun intended, edge AI, generative AI, TinyML.
Now's the time.
This is the frontier for folks to invest in. So,
and Pete and Davis, automotive, you said already, Davis, but it still surprised me, Meta. Maybe I'm wrong. Maybe it was a personal feeling, but back to 2018, 2019, I didn't feel that Meta was really interested at the edge. But what I saw today from Che, really, Meta is committed at the edge and is bringing innovation at the edge, starting with generative AI. I think it's very bold, the message.
Yeah, well, it's, if you kind of tie a couple of threads together, I mean, PyTorch is a common framework to develop and train these models, but the footprint of PyTorch is the framework itself, and the dependent libraries is pretty large. So when you're trying to port to a memory constrained board, it kind of begets this natural evolution from the team. So it's been great to see Executorch, and I think Chet alluded to it in the apps like Instagram and WhatsApp and Meta's apps. They are edge native, mobile, at least mobile native applications, right? Where data is created, the user interaction point. So while a lot of these big models live and train on servers still, they've been kind of catapulted into the future with the success of Llama and Llama 3.2 being a very popular model. I mean, we certainly see that a lot too. So no, I'm glad you brought it up. It's good to see.
Yeah, no, it's cool. Do you want to preview the talks tomorrow? If you want to bring up your slides, or you can add those in, maybe. Let's see.
Yeah.
That was today.
that was today, and tomorrow we will start once again 8 PST, short introduction, but then we will go through many 7 contribution from Hamza, Victor, Davis. Davis, you are on stage tomorrow. Looking forward to your great presentation. Ronan, Marek, Wasim, Jose, and then our usual recap. Tomorrow there will be really huge actors, ARM, Particle, ETH, NHP, and TII, and that's going to be a really interesting day too.
Oh yeah. The TII folks are going to talk about, they have that Falcon Mamba model that they built, foundational model for Edge. So that'll be really cool to hear that. And then from ARM, of course, and Particle has some new platforms that they are now shipping. Once he's going to talk about the Snapdragon-based platform that they're shipping.
Oh, cool.
Pretty cool. And I think also Wasim's going to show a project they've been working on called TinyRag, which is basically, it's a little bit, I wouldn't say off topic, but it's near topic. It's like an agentic AI for TinyML information. So they basically took all of the content from the TinyML community the past few years and created a big RAG. And you can ask it questions, and it's sort of like your one-stop shop if you wanted a TinyML.
That's awesome.
Not as good as Danilo, not quite, but
near human level,
kind of Danilo-like. So he's going to talk about how they built that thing, and I think we'll put it on we're going to have a new website coming up pretty soon. So it'd be fun to embed something like that in there, so people can kind of find answers to some of the content that we've had over the years. So.
Very cool.
I'm sure the content will be really inspiring and informative, and I think the community will really happy as maybe it was today to see how we are really interested in sharing and be together on this new challenge, which is GenAI. And GenAI at the edge is I feel that's my good feeling is going to be super fast.
Yeah. There's a couple of questions in the chat around availability. So all this stuff will be available on our YouTube channel once we get it all processed for future reference. And also, if you haven't been to the Discord channel, it's dsc.gg/edgegenai. There you go, event channel on Discord. We've got a bunch of people joined today. So and including the more detailed agenda, and we'll post some decks up there and some other slides and stuff. So those are 2 good locations. Other than that, I guess same time, same bat channel, same bat time tomorrow.
Perfect.
Stay with us tomorrow because the story is not ended, and then we are eager to hear from Davis as well as the other
That's
speakers.
the only reason.
One of the main reasons. Yes.
Great.
Yeah.
No, awesome. Fantastic start.
Good. Okay. Well, I will. I'm going to actually. It's a little housekeeping, but I'm actually going to keep the stream open for StreamYard reasons. But anyway, yes. Everyone in Europe, good night.
Bye. See you tomorrow.
In other time zones, have a good afternoon, and we'll see you tomorrow.